In the vast reaches of space, Alpha Centauri has captivated the human imagination for centuries. Its proximity, only 4.37 light-years from Earth, makes it our closest stellar neighbor, a place where the search for exoplanets has long intrigued astronomers and stargazers alike. Yet, despite this closeness, the Alpha Centauri system remained a mystery for decades. The question that haunted scientists for years remained: does Alpha Centauri harbor planets that could support life? In 2023, the James Webb Space Telescope, JWST, with its revolutionary design and unmatched sensitivity, was tasked with a seemingly impossible mission, peering into the heart of this star system and revealing its secrets. While JWST was originally built to explore the farthest corners of the universe, its advanced technology held promise to detect even the faintest signals from the nearby stars of Alpha Centauri. But there was a challenge: Alpha Centauri's extreme brightness, a feature that had thwarted previous attempts to detect planets in its vicinity. Yet what JWST found stunned the scientific community, sending ripples of excitement through space research. This discovery, something even the most optimistic scientists had only dared to dream of, could change the way we view our cosmic neighborhood. In this script, we'll break down exactly what JWST saw when it turned its lens toward Alpha Centauri, how it overcame the challenges of studying such a bright system, and what this groundbreaking discovery means for our search for life beyond Earth. As we venture deeper into the mysteries of Alpha Centauri, we'll explore the science, the challenges, and the excitement of this unprecedented astronomical achievement. What lies ahead in this distant yet tantalizing star system? The future of interstellar exploration and the potential for finding habitable worlds has just become more real than ever before. Chapter 1: The Quest for Planets Around Alpha Centauri. For centuries, humans have stared up at the night sky, captivated by the stars. Yet, of all the celestial bodies that fill our heavens, one star has captured the imagination of astronomers and dreamers alike: Alpha Centauri. As the closest star system to our own, Alpha Centauri sits just over 4 light-years away, a mere stone's throw in cosmic terms. This proximity has made it the subject of scientific fascination, and more recently, a target for some of the most advanced space missions ever conceived. Alpha Centauri is not just any star system. It is unique, representing the first logical destination for any future interstellar mission. Its 2 main stars, Alpha Centauri A and B, are Sun-like in their characteristics, with the same stellar types, temperature ranges, and energy output as our own Sun. This makes it an attractive candidate for understanding planetary systems similar to our own, and possibly even the conditions necessary for life. For decades, astronomers have asked the same haunting question: does Alpha Centauri have planets? The pursuit of this answer has been a long and frustrating one. Despite the proximity of Alpha Centauri, detecting planets around it has proven to be a challenge far greater than anticipated. The vast majority of exoplanet discoveries have been made around stars far more distant, where the brightness of the stars themselves is not an obstacle. But Alpha Centauri, despite its potential advantages due to its proximity, presents unique difficulties that have made planetary detection an elusive goal. Its extreme brightness has often overwhelmed sensitive telescopes, and its twin companion star, Alpha Centauri B, only complicates the situation further by flooding instruments with additional light. For over 70 years, astronomers tried and failed to find definitive proof of planets around Alpha Centauri. Multiple methods were employed, including the study of gravitational wobbles, which reveal the presence of massive planets by detecting slight movements of the star caused by its orbiting planet. Yet, Alpha Centauri continued to elude direct detection. The problem was not the lack of technology, but rather the nature of the system itself. Alpha Centauri's high luminosity made it a difficult target for traditional planet hunting techniques. Even the most sophisticated instruments could not overcome the overwhelming glare from the star itself. The search for planets around Alpha Centauri was defined by a series of false hopes, promising results that never quite materialized. Telescopes that were supposed to reveal new worlds instead produced nothing more than blurred images or inconclusive data. Yet, despite these setbacks, astronomers remained determined. The possibility that planets orbited Alpha Centauri was a tantalizing one, and the potential scientific implications were enormous. In 2023, a breakthrough came. The James Webb Space Telescope, JWST, the most advanced space telescope ever built, was tasked with making the seemingly impossible observation, detecting planets in the Alpha Centauri system. Designed to observe distant galaxies and the farthest reaches of the universe, the JWST was never intended to study the stars that populated our cosmic neighborhood. But astronomers, led by Charles Bickman at NASA's Jet Propulsion Laboratory, had a different vision. They believed that the JWST, with its unprecedented sensitivity and technological prowess, could overcome the limitations faced by previous attempts. They believed that, despite the challenges, the JWST could reveal the secrets of Alpha Centauri. The decision to direct JWST toward Alpha Centauri was not made lightly. Alpha Centauri is one of the brightest stars in the sky, and pointing a telescope like JWST at it seemed counterintuitive. The telescope was optimized to study faint objects, not glaring stars. It was designed to detect signals from distant galaxies, not from a star system that, in many ways, was too close for comfort. The brightness of Alpha Centauri posed the risk of damaging the telescope's sensitive detectors, which were finely tuned to capture light from galaxies billions of light-years away. But the scientific community was not prepared to let go of the dream of discovering planets around Alpha Centauri. For astronomer Charles Bickman, the desire to find a planet in our nearest stellar neighbor had been a lifelong ambition. He believed that if the JWST could make the impossible observation work, it would revolutionize our understanding of planetary formation, as well as the conditions necessary for life beyond Earth. His team's determination would eventually lead to a bold proposal: to use JWST's mid-infrared instrument, MIRI, to search for thermal emissions from potential planets. Instead of looking for the light reflected by planets, they would look for the heat emitted by those planets, a technique that was never attempted before with such a bright target. What made this mission so extraordinary was the approach. Alpha Centauri is a binary system, consisting of two sun-like stars. The presence of both stars posed significant challenges, as both emit intense light that would flood the telescope's detectors. JWST's solution to this problem was an ingenious one. The team decided to use a coronagraph, a tool that could block out the light from Alpha Centauri A, allowing the planet's faint thermal signal to emerge from the background. This would be a first, and it represented a bold leap forward in observational astronomy. Chapter 2: The Challenge of Finding Planets in Our Backyard. The search for planets around Alpha Centauri has been defined by one overriding difficulty: the system's extraordinary brightness. This, paradoxically, is both its greatest asset and its most insurmountable hurdle. As the closest star system to Earth, Alpha Centauri should have been the first stellar neighbor where planets were easily detectable. Yet astronomers have faced a nearly insurmountable challenge in capturing clear images of potential planets in the system. The problem lies not in the distance, but in the sheer intensity of Alpha Centauri's light. Unlike most stars that are so distant they appear as faint pinpricks in the night sky, Alpha Centauri is one of the brightest stars visible from Earth, particularly from the southern hemisphere. It shines with the brilliance of a beacon, overpowered by the light from its two primary stars, Alpha Centauri A and B. This radiance drowns out everything in its vicinity, making the detection of exoplanets nearly impossible. Imagine trying to detect the faint glow of a firefly next to a searchlight. The contrast is overwhelming, and the firefly's faint light simply vanishes in the glare. This is the fundamental issue astronomers face when trying to detect planets in the Alpha Centauri system. The brightness of Alpha Centauri A, which is the third brightest star in the sky, makes it extremely difficult to observe any objects in close proximity. It emits more than 50% more light than our Sun, and its luminosity makes it far more challenging to study than more distant stars. The intense light of Alpha Centauri A effectively drowns out the light reflected or emitted by any planets in orbit around it. While proximity to Alpha Centauri should theoretically make detecting planets easier, since nearby objects appear brighter and larger than distant ones, its brightness creates significant problems for planet-hunting telescopes. To put it simply, the star's light overwhelms the instruments designed to detect fainter sources of light. For astronomers, the problem becomes one of contrast. How can you separate a faint planetary signal from the overwhelming glare of the star itself? This challenge is compounded by the unique characteristics of the Alpha Centauri system. In addition to the brightness of Alpha Centauri A, the second star in the binary system, Alpha Centauri B, orbits close enough to Alpha Centauri A that its light also contaminates observations. The two stars move in an 80-year orbit around a common center of mass, coming as close as 11 astronomical units during their closest approach, and as far as 36 astronomical units at their most distant point. The proximity of these two stars to each other creates further complications for astronomers attempting to study planets orbiting Alpha Centauri A, as the light from Alpha Centauri B spills over and obscures any planetary signals. Even though Alpha Centauri is the closest star system to Earth, the task of detecting planets within it seemed, at least initially, beyond the reach of existing technology. Despite years of advancement in the field of exoplanet discovery, finding planets in such a bright system presented an unprecedented challenge. The conventional methods of detecting exoplanets, such as measuring the wobble of stars or detecting the dimming of light as planets transit in front of their stars, were ineffective in the face of Alpha Centauri's brilliance. Astronomers had developed a range of techniques to detect exoplanets in more distant systems. Gravitational wobbles, small movements of a star caused by the gravitational pull of an orbiting planet, had proven to be an effective method for detecting massive planets. The technique involves measuring the minute shifts in a star's position as it is tugged by the gravity of its planet. This method had been used to identify nearly 6,000 exoplanets, some of which were Earth-sized, orbiting stars hundreds of light-years away. However, Alpha Centauri's brightness made this technique virtually useless, as the star's immense light drowned out the subtle shifts caused by orbiting planets. Another widely used method is the detection of transiting exoplanets, where a planet passes in front of its host star, causing a brief but measurable dimming of the star's light. This technique had been instrumental in discovering thousands of planets across the galaxy, as it is particularly useful for detecting small planets in orbit around dimmer stars. But Alpha Centauri's light is so intense that any planet crossing its face would be nearly impossible to detect against the backdrop of such brightness. A more direct method of detection involves capturing the light emitted by planets themselves. Some of the most exciting discoveries in recent years have come from imaging exoplanets directly, using powerful telescopes to capture the faint glow of young planets orbiting distant stars. However, this method is even more challenging around Alpha Centauri, as its intense light not only swamps any signal from planets, but also distorts the instruments used to capture these faint emissions. Astronomers had long hoped that the proximity of Alpha Centauri would provide them with an edge in the search for exoplanets. The idea was simple. Because Alpha Centauri is so close, any planets orbiting it should appear larger and brighter than those in more distant systems. But the problem, as with so many things in science, was far more complicated than it first appeared. The extreme brightness of the system's two primary stars created a situation where the best technology available could not get the job done. For over 70 years, the question of whether Alpha Centauri had planets remained unanswered. Despite advances in technology, Alpha Centauri's brightness thwarted every attempt to find planets around its stars. As other exoplanet discoveries were made in more distant systems, The absence of a definitive answer about Alpha Centauri seemed frustratingly enigmatic. The answer, however, was just beyond reach, waiting for the right technology to unlock the secrets of our nearest stellar neighbor. Finally, in 2023, the James Webb Space Telescope, JWST, was tasked with taking up the challenge. Unlike previous telescopes, JWST was designed to capture the faintest signals from the most distant corners of the universe, and its capabilities were far beyond anything astronomers had previously worked with. While the task of observing Alpha Centauri seemed daunting, the JWST's advanced technology and unprecedented sensitivity offered hope where none had existed before. JWST was not designed to look at bright stars like Alpha Centauri. Its detectors were optimized for capturing light from galaxies billions of light years away, not from a system in our own backyard. But the promise of JWST's power and sensitivity was undeniable. If anyone could overcome the challenges posed by Alpha Centauri, it was JWST. Chapter 3: Proxima Centauri. While Alpha Centauri A and B have long captured the spotlight in the search for planets, the third star in the Alpha Centauri system, Proxima Centauri, has been equally intriguing to astronomers. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. Despite its lack of resemblance to the Sun, Proxima Centauri's proximity to Alpha Centauri A and B, roughly 13,000 astronomical units away, has made it a target of interest in recent years. It holds the title of being the closest known star to our solar system, located just 4.24 light-years from Earth. Unlike Alpha Centauri A and B, Proxima Centauri presents a different set of challenges. As a red dwarf, it emits much less light and is far dimmer than its Sun-like companions. This difference in luminosity makes it a less obvious target for planetary hunters. However, its extreme proximity to the Earth has drawn scientists' attention, as planets orbiting around such a star could potentially be located within reach of our current technological capabilities. For years, astronomers have speculated about the possibility of habitable planets around Proxima Centauri, but the star's unique characteristics complicate any meaningful comparisons to our own Sun. In 2016, Proxima Centauri garnered significant scientific attention when astronomers using the European Southern Observatory's Very Large Telescope, VLT, announced the discovery of an exoplanet orbiting within the star's habitable zone, the region where liquid water could exist on a planet's surface. This planet, designated Proxima b, was roughly the size of Earth and orbiting its star at a distance where conditions might allow for the presence of water, a key ingredient for life as we know it. The discovery of Proxima b raised many questions. Was it truly in the habitable zone? Could it host life? These questions sparked a wave of excitement in the scientific community. However, the conditions around Proxima Centauri are harsh, and the discovery of a habitable planet does not necessarily mean that life could thrive there. Proxima Centauri, like many red dwarfs, is known for its violent stellar flares, massive bursts of radiation that could strip away the atmosphere of a nearby planet, making it uninhabitable. In addition, Proxima b is tidally locked to its star, meaning one side of the planet always faces the star, while the other side remains in perpetual darkness. This could create extreme temperature variations, further complicating the potential for life. Despite these challenges, the discovery of Proxima b added a new dimension to our understanding of exoplanets in the Alpha Centauri system. It was the first potentially habitable planet discovered in our closest stellar neighborhood, and it highlighted the potential for finding similar worlds around stars that are much closer to Earth than the hundreds or thousands of light-years typically required to detect exoplanets. Proxima b's existence underscored the importance of studying nearby stars, and many scientists began to ask whether there might be more planets lurking in the Alpha Centauri system waiting to be discovered. The interest in Proxima b, combined with the wealth of knowledge gathered from previous exoplanet discoveries, fueled the drive to search for additional planets in the Alpha Centauri system. Alpha Centauri A and B were still the prime targets, as they are Sun-like stars, making them more likely to harbor planets with conditions similar to Earth's. However, the discovery of Proxima b served as a reminder that planets could exist in a wide range of stellar environments, including those that were previously considered inhospitable. This newfound interest in the Alpha Centauri system set the stage for a bold new phase in the search for exoplanets. While astronomers had long known that planets could be found orbiting distant stars, the idea that planets could exist in such proximity to our solar system was a game-changer. The possibility that Alpha Centauri, the nearest star system, could harbor planets with conditions similar to Earth raised the stakes for the entire field of exoplanet research. For decades, scientists had focused on more distant stars, which, while offering the possibility of interesting discoveries, were also far more challenging to study. The idea of finding a planet around Alpha Centauri, one of the brightest and most well-studied stars in the sky, was compelling. It promised to answer some of the most fundamental questions about planetary systems and their potential for habitability. Could a planet around Alpha Centauri A or B have conditions similar to those found on Earth? Could it support life? The discovery of Proxima b also prompted renewed interest in the possibility of interstellar travel. With Alpha Centauri as the closest star system, it represented the first real target for any future missions beyond our solar system. Proposals for interstellar missions, such as Breakthrough Starshot, began to take shape, with the goal of sending small, fast-moving spacecraft to Alpha Centauri in the hopes of gathering data from any planets that might exist there. However, even with the excitement surrounding Proxima b and the growing interest in Alpha Centauri, it was clear that more advanced technology would be required to make significant strides in studying the system. The tools available at the time were simply not capable of detecting the faint light from planets orbiting such bright stars. A new approach, with more sensitive instruments, was needed to uncover the hidden worlds of Alpha Centauri. This is where the James Webb Space Telescope, launched in 2021, would come in. With its unprecedented sensitivity and advanced technology, the JWST represented the best hope for overcoming the challenges of detecting planets in the Alpha Centauri system. JWST was designed to detect faint signals from the farthest reaches of the universe, and now astronomers were beginning to realize that its capabilities could be used to uncover the mysteries of our nearest stellar neighbor. By focusing on Alpha Centauri, scientists hope to finally answer the long-standing question: does this star system, the closest to our own, harbor planets? And if so, could some of those planets be similar to Earth? The discovery of Proxima b had already set the stage for the exploration of Alpha Centauri, but it was only the beginning. The search for planets in this system would require innovative thinking, advanced technology, and, above all, persistence. Chapter 4: Why Alpha Centauri became the holy grail of planetary discovery. Alpha Centauri has long been a source of fascination for astronomers. As the closest star system to our own, it represents humanity's first logical destination for any conceivable interstellar journey. But beyond its proximity, Alpha Centauri offers something even more tantalizing: the potential for planets that resemble our own solar system. The idea that Alpha Centauri could harbor planets with conditions similar to Earth's is not just an exciting scientific question. It touches on some of the most profound existential mysteries humanity has ever faced. Could we find planets with conditions suitable for life? Or perhaps more importantly, are we truly alone in the universe? Alpha Centauri consists of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, each with unique characteristics. However, the focus of much of the research has been on the 2 primary stars, Alpha Centauri A and B. These 2 stars are Sun-like, with masses, radii, and temperatures remarkably similar to our own Sun. For decades, scientists have speculated that planets orbiting these stars would experience conditions strikingly similar to Earth's, potentially making them suitable for life. The proximity of Alpha Centauri to Earth made it an ideal target for astronomers, who were eager to answer one of the most fundamental questions of modern science. Do planets orbit Sun-like stars? And if so, could they support life? The allure of Alpha Centauri as a planetary discovery target lies in its unique position in the cosmos. At just 4.37 light-years away, Alpha Centauri is the closest star system to Earth, making it the nearest possible host for habitable exoplanets. This closeness provides a unique advantage for astronomers attempting to detect exoplanets. Planets orbiting close stars such as Alpha Centauri are larger and brighter in the sky than those orbiting distant stars, making them easier to detect with advanced technology. This proximity, in theory, should make the discovery of planets in the Alpha Centauri system a relatively straightforward task, at least when compared to distant stars, which are far harder to study due to their distance and faintness. However, despite these advantages, Alpha Centauri has proven to be one of the most challenging targets in the search for exoplanets. The system's extreme brightness is both its greatest asset and its greatest obstacle. Alpha Centauri A, in particular, is a blazing, sun-like star that outshines all but two other stars in our night sky. It emits more than 50% more light than our Sun, which makes it a daunting object for planet-hunting instruments. The brightness of Alpha Centauri has overwhelmed every attempt to detect planets in the system using traditional techniques. The gravitational wobble method, which has been successful in detecting planets around distant stars, is ineffective in such a bright system. Similarly, the transit method, which measures the dimming of a star's light as a planet crosses in front of it, fails when the star itself is too bright. In addition to the brightness problem, Alpha Centauri's status as a binary star system creates further challenges. The two main stars, Alpha Centauri A and B, are locked in a wide orbit around a common center of mass. The two stars orbit each other every 80 years, coming as close as 11 astronomical units at their closest approach, and separating to as far as 36 astronomical units at their most distant point. This close proximity means that any potential planets in orbit around Alpha Centauri A or B would be subject to additional interference from the light of the companion star. In fact, the light from Alpha Centauri B, the secondary star in the system, floods the instruments that would be used to detect planets orbiting Alpha Centauri A, further complicating the search for planets in the system. Despite these challenges, Alpha Centauri remains an enticing target. The possibility that planets orbiting these two Sun-like stars could resemble Earth, or at least possess some of the characteristics necessary for life, is too significant for astronomers to ignore. The scientific potential of studying planets in the Alpha Centauri system is vast. If planets around Alpha Centauri A and B exist, they could offer astronomers a unique opportunity to compare the conditions of planets in a stellar system very similar to our own. This is not a theoretical exercise. It's the quest to find worlds that could harbor life, worlds that might someday be reachable by future generations. In addition to its proximity and Sun-like stars, Alpha Centauri is also a system that has held a special place in the cultural and scientific imagination. For centuries, Alpha Centauri has been the subject of speculation and hope. Ancient astronomers looked to the stars, wondering what worlds might exist beyond their own. In modern times, science fiction writers have long envisioned Alpha Centauri as the first destination for humanity's interstellar voyages. The idea that Alpha Centauri could be home to planets, potentially habitable ones, has only fueled the drive to explore this star system. The concept of life beyond Earth is one of the most fundamental questions in science. Since the discovery of exoplanets, astronomers have been searching for worlds that might harbor conditions similar to those found on Earth. While many exoplanets have been discovered, most orbit stars vastly different from our Sun. Planets around stars like red dwarfs or massive hot stars are often too extreme for life as we know it. The discovery of planets around Alpha Centauri A and B would be groundbreaking because these stars are so similar to our own Sun, and any planets orbiting them would receive radiation levels comparable to Earth's. This makes them prime candidates for the search for life, as planets in the habitable zone around these stars would experience conditions strikingly similar to those on Earth. Alpha Centauri is also one of the most studied star systems in history. It has been observed by astronomers for centuries, but only in recent years have we had the tools to make meaningful observations. Advances in telescope technology, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, have given astronomers the ability to look deeper into the system than ever before. These tools allow scientists to peer through the light of Alpha Centauri and search for planets that might be orbiting the system's stars. However, the challenge of detecting planets in this system has proved to be formidable, requiring new approaches and innovative thinking. The scientific community has been trying for decades to detect planets around Alpha Centauri. The fact that it has remained elusive speaks to the difficulty of the task, and yet, the potential rewards are enormous. Discovering a planet orbiting Alpha Centauri would not only help us understand the formation and evolution of planetary systems, but it could also provide insight into the potential for life beyond Earth. As astronomers continue their search, the possibility of finding a planet in this nearby system remains one of the most tantalizing scientific goals of our time. Chapter 5: A groundbreaking tool for planet hunting. The James Webb Space Telescope, JWST, represents the pinnacle of astronomical engineering. As the most powerful space telescope ever built, JWST was designed to explore the farthest reaches of the universe and provide unprecedented insights into the cosmos. Its capabilities are not limited to distant stars, though. JWST is also set to revolutionize the study of exoplanets. Its unprecedented sensitivity makes it a prime candidate for solving some of the most challenging problems in planetary science, particularly in systems like Alpha Centauri. Unlike its predecessor, the Hubble Space Telescope, JWST was designed to focus on the infrared part of the electromagnetic spectrum. Infrared astronomy allows scientists to detect heat, making it ideal for studying the thermal emissions of planets. Planets emit their own infrared light, which can be detected even when the planet itself is too faint to be seen in visible light. This is especially useful when studying planets orbiting bright stars like Alpha Centauri, where reflected light would be drowned out by the star's brightness. JWST's mid-infrared instrument, MIRI, is at the heart of its exoplanet hunting capabilities. MIRI observes objects in the mid-infrared range, which is useful for studying planets that have cooled over time, such as older, potentially habitable worlds, like those around Alpha Centauri. MIRI allows astronomers to detect thermal emissions from planets that are too faint for visible light observation. In the case of Alpha Centauri, the thermal emissions from planets orbiting the stars could provide the first clues to their composition and atmospheric conditions. However, using JWST to study Alpha Centauri posed a challenge. Alpha Centauri is one of the brightest stars in the sky, and its light can overwhelm the sensitive detectors on board JWST. To overcome this, JWST uses a coronagraph, a device that blocks out the light from the central star while allowing fainter objects like planets to pass through. This technique, called starlight suppression, is essential for making exoplanet detections in systems with bright stars like Alpha Centauri. JWST's coronagraph is designed for high-contrast imaging, making it possible to block out the overwhelming light from Alpha Centauri while preserving faint planetary signals. Despite the promising concept, using JWST to study Alpha Centauri was not without its risks. The extreme brightness of Alpha Centauri A, combined with the motion of the star across the sky, presented significant challenges to precise pointing. JWST was designed to study distant galaxies and faint cosmic objects, not stars moving across the sky. The rapid motion of Alpha Centauri meant the telescope had to continuously adjust its position to keep the star centered behind the coronagraph's mask. Any errors in positioning could lead to the leakage of starlight, ruining the observations. In addition, Alpha Centauri is part of a binary system, with Alpha Centauri B orbiting relatively close to Alpha Centauri A. The light from Alpha Centauri B complicates matters further, spilling over into the coronagraphic field and contaminating the image. JWST's coronagraph was not designed to block light from two stars simultaneously, and finding a solution was a key challenge for the mission. The team had to develop new strategies to mitigate this issue and ensure that the telescope's instruments wouldn't be overwhelmed by the combined brightness of the two stars. The JWST team knew the challenges of observing a bright star like Alpha Centauri. Many astronomers initially dismissed the idea of using JWST to study the system, fearing it would damage the telescope's detectors or produce unusable data. But Charles Bickman, a veteran astronomer at NASA's Jet Propulsion Laboratory, refused to accept these concerns. He believed JWST had the potential to make groundbreaking discoveries even in such a challenging system, and assembled a team of researchers determined to push the telescope to its limits. Bickman's team proposed a novel observation strategy. Use JWST's mid-infrared instrument, MIRI, to search for thermal emissions from potential planets around Alpha Centauri A. Instead of focusing on reflected starlight, they would look for the heat emitted by the planets themselves. This approach, known as thermal emission detection, is particularly effective for older planets that have cooled down over time. For planets orbiting Sun-like stars like those in the Alpha Centauri system, this technique was promising. Planets in Alpha Centauri A's habitable zone would be expected to have temperatures between 200 and 350 Kelvin, emitting thermal radiation at wavelengths where MIRI achieves its peak sensitivity. To make this work, the team needed to block the light from Alpha Centauri A. The coronagraph onboard JWST's MIRI was crucial for this. It works by placing a physical mask, called a four-quadrant phase mask, over the star's position on the detector. This mask creates an artificial eclipse, suppressing the star's light while allowing fainter planetary signals to emerge. JWST's coronagraph is the only instrument capable of achieving the necessary starlight suppression to detect faint planetary signals near such a bright star. Success relied on overcoming the extreme brightness of Alpha Centauri A, the star's motion, and contamination from Alpha Centauri B. The team spent months developing custom observation sequences, refining the coronagraph's performance, and simulating potential outcomes. It was clear that this would be an extraordinary effort, pushing JWST beyond its designed capabilities. But the potential rewards were too great to ignore. If JWST could observe Alpha Centauri, it would provide the first direct imaging of planets orbiting a Sun-like star within our closest stellar neighbor. Chapter 6. JWST's first attempt to capture Alpha Centauri. With years of planning, simulations, and meticulous preparation behind them, the team behind the JWST's mission to study Alpha Centauri was ready for their first attempt. The stakes were enormous. If the telescope could successfully observe the Alpha Centauri system and detect any potential planets, it would mark a revolutionary achievement in exoplanet science. The first observations, however, were far from straightforward, and the initial results would leave the team with more questions than answers. The first challenge was to achieve precise targeting. JWST had to be carefully aligned to capture Alpha Centauri A without overloading its sensitive detectors. As discussed earlier, Alpha Centauri A is one of the brightest stars in the sky, emitting more than 50% more light than our Sun. Its light was so intense that even slight errors in positioning could cause the telescope to miss the target, flooding its detectors with unmanageable light. To prevent this, the team employed a strategy called blind offsetting. Instead of directly pointing the telescope at Alpha Centauri A, JWST first acquired a nearby reference star of manageable brightness, Epsilon Musca, located approximately 330 light-years away. This allowed JWST's guidance systems to lock onto a star with brightness that wouldn't overwhelm its detectors. Afterward, the telescope performed a calculated offset, effectively shifting its focus to Alpha Centauri A without directly pointing at it. This clever workaround allowed JWST to bypass its brightness limitations, and positioned the star behind the coronagraphic mask for observation. As the first observations began, there was an air of anticipation. The team had every reason to believe that their strategy would work. JWST's advanced instruments were capable of detecting the faintest signals, even from a bright star system like Alpha Centauri. The coronagraph, designed specifically to block out starlight while allowing planetary signals to pass through, was expected to function optimally, even under the challenging conditions of Alpha Centauri's overwhelming light. The stakes couldn't have been higher, and everyone knew that the success of this mission would have profound implications for the future of exoplanet research. The first set of data was collected, and the team anxiously awaited the results. As the raw images were transmitted back to Earth, it quickly became clear that the data wasn't what they had expected. The images were chaotic, filled with light contamination, diffraction patterns, and artifacts from the coronagraph's efforts to block the star's light. Alpha Centauri b, the companion star in the binary system, was visible in the upper part of the image, casting its own brilliant light across the field of view. The coronagraph had done its job of suppressing Alpha Centauri a's light, but the contamination from Alpha Centauri b rendered the images almost unusable. The team had their work cut out for them. The initial failure was a setback, but it did not deter the team. They knew that the road to success would not be easy. The first observations were an important step in learning how to improve their approach and refine the telescope's methods. The team immediately began analyzing the data to determine what went wrong and what could be done differently in future observations. Despite the disappointing results, the team remained hopeful. They had known from the outset that observing Alpha Centauri would be a monumental challenge, but they were committed to solving the problems and pushing JWST's capabilities to the limit. In the weeks following the first observations, the team regrouped and revised their strategy. They re-examined the pointing accuracy, analyzed the contamination from Alpha Centauri b, and refined their data reduction methods. The coronagraph had worked, but the presence of Alpha Centauri b in the field of view had complicated the observations. The team implemented new techniques to handle the contamination and improve the quality of the data. They also adjusted the telescope's pointing procedures, fine-tuning the offset to account for the star's motion and ensure better alignment. By mid-2024, the team felt confident that they had solved many of the issues that had plagued the first round of observations. The revised strategies had been tested in simulations and were now ready for another attempt. The telescope was pointed back toward Alpha Centauri A, this time with a new sense of purpose and determination. This second round of observations would prove to be a critical moment in the mission. After weeks of anticipation, the results of the second observation campaign began to come in. This time, the data were much clearer. The coronagraph had successfully suppressed Alpha Centauri A's light, and the contamination from Alpha Centauri b was significantly reduced. The images were still not perfect, but the improvements were undeniable. The team was excited to see clearer signals emerging from the data, and for the first time, they could begin to see the faint thermal emissions from a potential planet orbiting Alpha Centauri A. The faint dot of light that appeared in the processed images was enough to make the scientists sit up and take notice. While the signal was not conclusive, it was highly suggestive of something truly groundbreaking: a potential exoplanet orbiting Alpha Centauri A. The team had long suspected that planets might exist around the Sun-like stars in the Alpha Centauri system. But now they had their first real evidence. The object, designated S1, was more than 10,000 times fainter than its host star, but it appeared in the expected location, at a distance of about 1.5 arcseconds from Alpha Centauri A. The signal had a statistical significance of 5.5 sigma, meaning the probability that the observed signal was a random fluctuation was extremely low, less than 1 in 10 million. The team immediately began follow-up observations to confirm their findings. They knew that extraordinary claims required extraordinary evidence, and they were determined to ensure that S1 was indeed a planet and not some other celestial phenomenon. The early results were promising, but further observations would be needed to confirm whether this was truly a planet or just an artifact of the data. The first confirmation attempt came in early 2025, when the team returned to the Alpha Centauri system for another round of observations. They used the same techniques, analyzing the data for any changes in the position of the object that would confirm its motion in orbit around Alpha Centauri A. The results, however, were unexpected. S1 had disappeared. The object that had appeared so clearly in the previous observations was no longer visible. For weeks, the team struggled to make sense of the disappearance. The planet, if it existed, had vanished from view. Chapter 7: The Vanishing Planet. The unexpected disappearance of S1, the potential exoplanet observed in Alpha Centauri A's habitable zone, left the scientific community baffled. A signal that had initially seemed so promising, appearing with 5.5 sigma statistical significance, had suddenly vanished from the images. This was not what anyone had expected. In the world of astronomical observations, the absence of a detected object doesn't always imply a failed discovery. It can also signify something far more complex. The search for S1 was far from over, and its disappearance only added to the intrigue, propelling astronomers to dive deeper into what might be happening in the Alpha Centauri system. The team knew that planets do not simply vanish. Gravitationally bound objects orbiting stars follow predictable paths governed by Newton's laws of motion and Einstein's refinements. If S1 had been a genuine planet, it should have appeared in subsequent observations, even if its position shifted as it moved in its orbit. Instead, the planet seemed to have completely disappeared from view, which led to a series of important questions. Was S1 ever a real planet to begin with? Could it be a distant background object, an asteroid, or something else entirely? Or was it simply a fluke, a one-off signal that, despite its apparent statistical significance, was nothing more than a random fluctuation? The first possibility that was considered was the idea that S1 had never existed in the first place. The faint signal detected in August 2024 could have been a statistical fluke, an improbable event in the vast sea of data that mimicked the appearance of a planet. After all, electronic detectors measuring faint signals are not immune to random noise and quantum fluctuations. The scientific team spent considerable time analyzing the data from every possible angle, attempting to determine if the initial detection could have been caused by an error in the instruments, an anomaly in the data, or an unusually rare random fluctuation. However, this explanation seemed highly unlikely. The 5.5 sigma significance of the detection meant that the probability of the signal being a result of random noise was less than 1 in 10 million. It seemed extraordinarily improbable that such a significant signal could have been a mistake. Furthermore, when the team split the August data into independent portions, they found that both halves showed the same signal, at the same location, and with the same brightness. This level of consistency across independent data samples was not characteristic of random noise. The signal had passed every test the team had devised to distinguish genuine astronomical sources from statistical flukes. The next possibility considered by the team was that the object detected in August 2024 was not a planet, but instead a background object, a distant galaxy perhaps, or a faint star that appeared in the same region of the sky as Alpha Centauri. This idea was given serious consideration, as it was known that astronomical images can sometimes capture objects from distant backgrounds that appear to be closer than they actually are. However, after cross-referencing the location of the detected signal with known catalogues of background sources, the team found no matches. No previously identified object was in the area where the signal had appeared. Additionally, the spectral characteristics of the detected light were consistent with a planet rather than a background galaxy or star. Background galaxies typically show different color signatures than planets, and the wavelength distribution of the signal matched what would be expected from a cool, thermally emitting planet. With these possibilities ruled out, the team was left with a third and far more intriguing possibility, that S1 was a real planet, but that it had moved to a position where it was no longer detectable by the current instruments. This explanation involved a deeper understanding of orbital mechanics and the limitations of coronagraphic sensitivity. In high-contrast imaging, such as that used by JWST, there are regions where detection is possible and regions where it is not. Planets orbiting close to their stars, for example, are often too close to be detected because the coronagraph cannot block out the overwhelming light from the star in those regions. Likewise, planets too far away from their stars are too faint to detect because their thermal emissions become too weak to register. S1 appeared to occupy a region of space that was on the edge of coronagraphic sensitivity. The planet's distance from Alpha Centauri A was approximately 1.5 arcseconds, which corresponds to about 2 astronomical units. This position was close enough for detection, but as the planet moved in its orbit, it might have moved into a region where the coronagraph could no longer block out the star's light effectively. The deflected light from the star creates a halo around the coronagraph, and in certain parts of the image, this halo is too strong for any faint planetary signals to emerge from the glare. What was particularly puzzling about S1's disappearance was that it had been clearly detected in August 2024, but by February and April 2025, the planet was nowhere to be found. The planet's orbital motion could explain the shift in its visibility. If S1's orbit was elliptical, it would naturally move closer to Alpha Centauri A at certain points in its orbit, making it more difficult to detect. At other points, it would move farther away from the star, where it could be more easily observed. This shifting visibility pattern could account for why S1 was detected in one observation but disappeared in the next. The possibility of orbital mechanics governing S1's disappearance was supported by simulations that the team ran using known parameters of the Alpha Centauri system. These simulations suggested that S1's orbit could have an eccentricity of around 0.4, which means that its distance from Alpha Centauri A would change considerably over the course of its orbit. Such a configuration would explain the planet's temporary disappearance from view in early 2025, as it moved closer to the star during certain phases of its orbit, where coronagraphic sensitivity was insufficient for detection. The team also noted that the current observations had not yet covered the full span of the planet's orbit, so the possibility remained that S1 would return to detectable positions in future observations. Chapter 8. Revisiting Alpha Centauri for confirmation. After the disappearance of S1, the potential exoplanet observed in Alpha Centauri A's habitable zone, the scientific community was left with mixed emotions, hope and skepticism. While the initial detection in August 2024 was promising, the subsequent non-detections in early 2025 raised doubts. However, the possibility that S1 was a real planet persisted, and the team behind the observations was determined to find the definitive answer. With new strategies in place, the team prepared for a critical follow-up observation campaign in mid-2025, aimed at confirming or refuting the planet's existence. The stakes were high. If S1 was confirmed to be a planet, it would become the closest exoplanet ever detected orbiting a Sun-like star, just 4.37 light-years from Earth. The implications for astrobiology, planetary science, and our understanding of the universe would be profound. But the task ahead was monumental, requiring refined observation techniques and innovation to overcome the challenges posed by Alpha Centauri's brightness and motion. In preparing for this next observation window, the team revisited their methods for dealing with Alpha Centauri A's extreme brightness. Their original coronagraphic approach had worked to a degree, but the contamination from Alpha Centauri B had been persistent. They planned to refine their technique for separating the light from both stars, isolating Alpha Centauri A more precisely, while further mitigating interference from Alpha Centauri B. They also fine-tuned their pointing precision to account for the star's rapid motion. With a new round of simulations and adjustments to the telescope systems, the team aimed to maximize coronagraph sensitivity and improve their chances of detecting the planet. The new campaign, set for mid-2025, relied on the same strategies that had worked for the initial detection, but with improvements based on lessons learned from the previous failures. The plan was to observe Alpha Centauri A over several long exposure sequences, each lasting hours, focused on capturing any faint signals from the suspected planet. The team had learned valuable lessons from the first attempts and now understood the precise limitations of the coronagraph. They also developed new methods for reducing contamination from Alpha Centauri B, improving the quality of the data. The first few images that returned to Earth were promising, but still fraught with challenges. The data showed signs of contamination from both Alpha Centauri A and B, but the team was prepared to handle it. They employed new data reduction techniques involving reference star subtraction and advanced algorithms like principal component analysis to strip away the noise and reveal potential planetary signals. Despite the chaos in the raw images, the refined methods allowed for clearer analysis. As the weeks passed and more data were collected, small hints of something extraordinary emerged. A faint signal appeared in the processed images. This time, it wasn't a single point of light, but periodic variations in brightness that seemed to match the expected position of S1. While still too faint to conclusively confirm a planet, the patterns resembled those observed in the August 2024 data. The team began to believe they were seeing something real. However, the question remained, was S1 a planet or something else? To confirm its nature, they needed to prove that the object's motion matched a planetary orbit. By comparing the current data with the August 2024 observations, they could begin to trace its movement around Alpha Centauri A. The key was to show that S1's position changed over time, consistent with gravitational binding to the star. With the final observation window in August 2026 approaching, the team prepared for one last attempt to confirm S1 as a planet. They needed to capture the planet's movement at the right moment. If S1 reappeared in the predicted position, it would provide overwhelming evidence of its planetary nature. If it didn't, the mystery would deepen. The August 2026 observation would be the final test. If S1 was detected at the expected location, it would confirm the presence of a planet orbiting Alpha Centauri A. If not, it would leave the scientific community with more questions than answers. But regardless of the outcome, the process would have demonstrated the extraordinary power of JWST and the ingenuity of the scientists pushing its limits. Chapter 9. Final Confirmation or Deepening Mystery. As August 2026 approached, the scientific community was on edge, waiting for the final confirmation that could either solidify the discovery of S1 as a planet or cast it into the realm of mysteries. The anticipation was palpable. This would be the third and potentially final observation window, and it would either confirm S1's existence or expose the discovery as a fluke. The implications of the outcome could fundamentally alter our understanding of exoplanet detection, stellar dynamics, and even the potential for life beyond Earth. The significance of this observation was immense. If S1 was confirmed as a planet, it would be the closest exoplanet ever found orbiting a Sun-like star, just 4.37 light-years away from Earth. This proximity would provide unprecedented opportunities for studying the planet's atmosphere, composition, and possibly even signs of habitability. Additionally, the implications for future space missions targeting Alpha Centauri and similar systems would be profound. Interstellar exploration, once considered science fiction, could take on a more practical trajectory with the discovery of nearby habitable zones. But the road to confirmation was fraught with challenges. The primary issue was still the extreme brightness of Alpha Centauri A, which continued to overwhelm the sensitive detectors on the James Webb Space Telescope. Even though the team had refined their coronagraphic techniques, the difficulty of distinguishing planetary signals from stellar glare persisted. The first major hurdle was ensuring that the telescope could lock onto the target with the necessary precision. The continuous motion of Alpha Centauri, along with the contamination from its binary companion, Alpha Centauri b, created a dynamic environment that required constant adjustments to the telescope's pointing system. In fact, the team had to account for the star's movement and adjust for its parallax effect, making each observation a highly complex task. Fortunately, the team's previous experience with the 2024 and early 2025 observations had provided them with the expertise and confidence to deal with these issues. They had refined their tracking systems, improved their pointing accuracy, and developed new data reduction algorithms that allowed them to filter out contamination more effectively. By 2026, they had created a highly refined observation sequence that would allow JWST to observe Alpha Centauri A with unprecedented precision. When the first observations for the 2026 campaign began, the team was cautiously optimistic. As the data began to stream in, the team could see that the improvements they had made were paying off. The images were cleaner, with less contamination from Alpha Centauri b, and the coronagraph was functioning at its best. But even with these improvements, the true test was whether or not S1 would reappear in the expected location. In the early stages of data processing, it was clear that the object seen in August 2024 had not returned to the same position. The images were still filled with noise, and the faint signal that had once been so prominent was nowhere to be found. The data processing algorithms quickly identified that the expected position of S1 was not visible. The team, now well versed in these complications, did not jump to conclusions. Instead, they began running additional simulations and data reduction tests to ensure that the absence of the signal was not due to a misalignment or some other technical issue. After a few weeks of intense scrutiny and reanalysis, the team came to a startling conclusion. The planet had indeed vanished. Despite the improvements in their techniques, S1's signature was missing from the data, and the faint signal that had once been detected in August 2024 could not be found in the 2026 images. The team was stunned. This was not supposed to happen. S1 had been expected to reappear at the predicted location based on its orbital motion, yet it seemed to have vanished entirely. The absence of the signal was not just an anomaly, it was a scientific conundrum. The team was left wondering whether the planet's orbit was more complex than they had anticipated, or if some other factor was at play. They had already accounted for S1's eccentric orbit, which had caused its disappearance in early 2025, but they had not expected it to disappear so completely in this final observation window. There were many theories about what might be happening, but no clear answer. One possibility was that the planet had moved to a region of its orbit where it was no longer detectable due to coronagraphic sensitivity limits. JWST's coronagraph works by blocking out the overwhelming light from the central star, but it is not perfect. If the planet had moved too close to Alpha Centauri A, the coronagraph could no longer suppress the star's light enough to detect the planet. On the other hand, if the planet had moved farther away from the star, it might have become too faint to be detected by the telescope. Another theory was that S1 was never a planet at all. Despite the statistical significance of the initial detection, the possibility that it was an artifact of the data could not be ruled out entirely. The team had tested for every known error, and all tests had passed, but there was still the possibility of some unknown factor that had caused the initial signal. Perhaps S1 had been a transient event, a temporary fluctuation in the data that mimicked the signature of a planet, but was not actually an exoplanet. As the team pondered these possibilities, they realized that the outcome of the 2026 observation campaign might not lead to definitive confirmation of S1's existence. Instead, it could raise even more questions, leaving the scientific community with a mystery that might never be fully solved. The team also acknowledged that this was part of the scientific process. discoveries do not always follow a linear path, and sometimes the pursuit of answers leads to more questions. Despite the uncertainty, the results of the 2026 campaign were far from a failure. The search for exoplanets is a complex and evolving field, and the techniques developed for this observation would have far-reaching implications for future missions. The ability to observe distant planetary systems with such precision would enable astronomers to explore other nearby stars in unprecedented detail. The lessons learned from Alpha Centauri would inform the design and execution of future exoplanet surveys, enabling scientists to push the boundaries of what is possible in planetary discovery. In the end, the 2026 campaign may not have provided the definitive answer the team was hoping for, but it opened up new avenues of inquiry and strengthened the case for future exoplanet observations. Regardless of whether S1 was confirmed as a planet, the campaign highlighted the remarkable capabilities of JWST and the extraordinary dedication of the team behind the mission. The scientific journey to explore Alpha Centauri was far from over, and the discovery of new worlds, whether in this star system or others, would continue to shape humanity's understanding of the universe. Chapter 10: The Final Verdict. As August 2026 drew closer, the anticipation reached a fever pitch. The final opportunity to confirm or debunk S1 as a planet was now upon the scientific team. Every astronomer, every researcher who had worked on the project for years, hoped that this would be the moment when everything fell into place. After months of technical adjustments, refined strategies, and iterative observations, the team was ready to make one last attempt at confirming their discovery. But as the data began to pour in, it was clear that the final chapter of this saga would take an unexpected turn. The latest round of observations initially appeared promising, but as the team sifted through the raw data, they faced a familiar issue. The anticipated position of S1, the planet that had caused such excitement in 2024, was nowhere to be found. At first, it seemed like a repeat of the February 2025 non-detection, but with a crucial difference. This time, the data was thoroughly scrutinized, analyzed, and processed with every imaginable adjustment, yet the result remained the same. S1 was missing. The team had used all their available knowledge, from sophisticated data reduction algorithms to advanced orbital simulations, to predict where the planet would be. But despite their best efforts, the object that had once been seen with 5.5 sigma significance in 2024 seemed to have disappeared without a trace. The team was faced with an uncomfortable reality. Perhaps S1 was never a planet at all. The disappearance of S1 raised a host of questions that had yet to be answered. Could the object have been a transient signal, one that only briefly mimicked the characteristics of a planet before fading into the noise? Could the data have been misinterpreted, or was there some other factor that caused the signal to vanish? The team went back to the drawing board, looking for answers to these new, troubling questions. One possibility that was raised was that the object observed in August 2024 was never a planet, but rather an artifact of the data, an improbable fluctuation that could have mimicked a planetary signal but had no real astronomical origin. The signal had passed rigorous tests, but there was still the possibility that it was a statistical anomaly. The scientific community had already seen cases where faint, seemingly significant signals turned out to be nothing more than noise, and this potential explanation was hard to ignore. On the other hand, there remained the possibility that S1 was indeed a planet, but that it had simply moved to a position beyond the reach of JWST's coronagraphic sensitivity. Given its highly eccentric orbit, it was possible that S1 was now in a phase of its orbit where it was no longer visible from Earth. This possibility made sense, especially considering that the object had shown up in 2024 but was now absent from the 2026 observations. The planetary motion theory remained consistent with the orbital parameters derived from previous data. As the weeks passed, the team delved into the data once more, running simulations and refining their models. They re-examined the initial detection, the calculations that had led to the August 2024 conclusion, and all the follow-up data. They also took a deeper look at the possibility that S1 was part of a system that had an extremely complex orbital architecture. Perhaps multiple planets in the Alpha Centauri system, each with their own eccentric orbits, were interacting in ways that complicated the detection of S1. If there were additional planets that hadn't been detected yet, they might provide the key to understanding what was happening. At the same time, the team began investigating alternative explanations. Could S1 have been a background object that was mistakenly identified as a planet? The team had previously ruled out the possibility of this happening, but with the continued absence of the signal, they were forced to reconsider. The sheer proximity of Alpha Centauri meant that even the faintest background object could appear to be in the same field of view. However, after further examination of the data and cross-referencing with background star catalogues, no new candidates emerged that could explain the signal. The final decision came in late 2026, after months of back-and-forth deliberation. The team, while hesitant to draw conclusions, was forced to admit that they might have been wrong about the initial detection. There was still a chance that S1 was a planet, but the evidence was no longer strong enough to confirm it with certainty. What the team had learned, however, was just as valuable. They had tested the limits of JWST's coronagraphic techniques and had pushed the boundaries of what was possible in terms of exoplanet detection. The challenge of observing planets in such a bright and complex stellar system had provided new insights into how to detect planets around other stars. Despite the uncertainty surrounding S1, the team's work had opened up a new frontier in exoplanet science. The lessons learned from Alpha Centauri could be applied to other stellar systems, and the techniques developed to observe the Alpha Centauri system would help astronomers in their search for planets around other nearby stars. Even if S1 wasn't confirmed, the journey had provided valuable data and insights that would shape the future of exoplanet research. In the end, the mystery of S1 remains unsolved, but the search for answers continues. The final verdict on whether S1 is a planet or whether it was a fluke remains elusive, but the journey to uncover the truth has advanced humanity's understanding of the cosmos in ways that will ripple across the field of astronomy for years to come. Whether S1 exists or not, its discovery, however fleeting, has cemented its place in the annals of exoplanet history. The mission to Alpha Centauri will not be forgotten, and the quest for planets around sun-like stars will continue to captivate and inspire future generations of scientists and explorers. Chapter 11: The Future of Exoplanet Discovery. The journey to confirm S1 as an exoplanet may have reached an unresolved conclusion, but the story of exoplanet discovery is far from over. The challenges faced during the search for S1 in Alpha Centauri have provided astronomers with invaluable insights that will shape the future of planetary science for decades to come. If S1 was a fluke, a random noise that mimicked the characteristics of a planet, then the lessons learned from its detection will help refine techniques for distinguishing real planetary signals from those created by artifacts. If AS1 is eventually confirmed, its discovery will be remembered as a landmark moment in the search for exoplanets, one that pushed the limits of astronomical technology and human ingenuity. Regardless of the outcome for S1, the James Webb Space Telescope, JWST, has already proven itself to be a transformative tool in exoplanet discovery. Since its launch, JWST has revolutionized our ability to observe distant worlds, with its unparalleled sensitivity and advanced imaging capabilities. The success of JWST's coronagraphic techniques in observing Alpha Centauri A, despite the challenges of extreme brightness and stellar motion, opens up new possibilities for future missions targeting other star systems. While Alpha Centauri is the closest and most studied neighboring stellar system, it is far from the only one that holds the potential to host planets capable of supporting life. There are thousands of nearby stars, many of which are sun-like, just waiting to be observed. The future of exoplanet science will see a shift toward examining systems that are within reach, systems where planets may be detected and studied in greater detail than ever before. JWST's advancements in observing planets around bright stars will be a crucial stepping stone for these missions. One key aspect of future exoplanet discoveries is the quest for planets in the habitable zone, the region around a star where conditions may be just right for liquid water to exist on the surface. The discovery of a planet in the habitable zone of a star is one of the most profound goals of modern astronomy. Alpha Centauri A, with its sun-like characteristics, offers an exceptional candidate for such a search. Although S1, the potential planet, was likely a gas giant, the possibility remains that it could have moons in its habitable zone, which would be even more exciting. If S1 does host moons with conditions suitable for life, the implications for astrobiology would be groundbreaking. But finding planets in the habitable zone of nearby stars isn't a simple task. As seen in the case of Alpha Centauri, bright stars and complex stellar systems present unique challenges that require innovative solutions. However, JWST's advancements in coronagraphy, coupled with its ability to capture faint signals from nearby stars, sets the stage for future discoveries in the search for habitable worlds. The methods developed for Alpha Centauri will be applied to other nearby stars, leading to the discovery of planets that were once considered too difficult to detect. The success of future missions will also depend on improvements in imaging technology. While JWST has taken giant leaps forward, its capabilities are still limited by factors such as coronagraphic sensitivity, stellar contamination, and the dynamic nature of stellar systems. The next generation of space telescopes, including the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory, will push these boundaries even further. These telescopes will have the ability to directly image Earth-like planets and analyze their atmospheres for signs of habitability. The upcoming telescopes, with their more advanced coronagraphic systems and higher resolution, will be able to examine distant worlds in greater detail, potentially detecting gases like oxygen and methane that could indicate biological activity. Ground-based observatories, too, are playing a crucial role in the future of exoplanet science. The Extremely Large Telescope, ELT, currently under construction in Chile, will have a primary mirror that is 39 meters in diameter, surpassing JWST's ability to capture faint planetary signals. ELTs will work in tandem with space-based telescopes, providing complementary data that will help refine our understanding of exoplanets. These ground-based observatories will be able to track exoplanets with greater precision, and their advanced spectroscopic instruments will allow for detailed analysis of planetary atmospheres. The integration of both space-based and ground-based technologies will open up new opportunities for discovering and studying exoplanets. This combination of tools will enable astronomers to detect smaller planets, even those in the Earth's size range, and to analyze their atmospheric compositions with greater precision. While we are still in the early stages of this research, the data gathered from future observations will undoubtedly transform our understanding of the universe. Beyond simply detecting planets, the focus of future missions will shift toward understanding their nature. Are they Earth-like worlds with rocky surfaces and conditions suitable for life? Or are they gas giants hostile to any form of life as we know it? As we detect more exoplanets, we will begin to characterize their atmospheres, compositions, and potential for habitability. This will involve identifying the key ingredients for life: water, an atmosphere, and a stable climate, and determining whether they exist in any meaningful way on other planets. The ultimate goal of exoplanet science is to answer one of humanity's most profound questions: are we alone in the universe? If other habitable planets exist, could they harbor life? And if so, what might that life look like? This quest for answers has been a driving force in astronomy for centuries, and now, with the advent of powerful telescopes like JWST, the possibility of finding life beyond Earth is closer than ever. The discovery of life elsewhere in the universe would be a momentous event, reshaping our understanding of biology, evolution, and the very nature of existence. Even if we do not find life immediately, the search for habitable worlds will continue to inspire generations of scientists, engineers, and explorers. The technologies being developed to search for exoplanets will undoubtedly have broad applications, advancing our capabilities in fields such as remote sensing, data analysis, and even interstellar travel. In the end, the mystery of S1 may not have been resolved, but it has sparked a wave of interest and excitement in exoplanet research. It has shown the world that we are capable of achieving things once thought impossible, and that the search for other worlds will continue to drive innovation and exploration. The journey to discover life beyond Earth is only just beginning, and the tools we've developed will guide us toward new discoveries, new questions, and new answers that will shape the future of humanity's understanding of the cosmos. Chapter 12: Interstellar Exploration and Humanity's Future. The search for exoplanets is more than just a scientific endeavor. It represents humanity's drive to understand its place in the cosmos. With each new discovery, we move closer to answering one of our oldest questions: are we alone? As astronomers refine their techniques and technology to find more distant planets, the dream of interstellar exploration continues to grow. The implications of discovering exoplanets like S1 around Alpha Centauri go far beyond planetary science. They have the potential to reshape humanity's future. The closest star system to Earth, Alpha Centauri, has long been an object of fascination. For centuries, it has symbolized the possibility of interstellar travel, our first true destination beyond the solar system. And with the discovery of S1, that possibility is no longer the stuff of science fiction. While the technology to send humans to Alpha Centauri is still in the conceptual phase, the detection of exoplanets in such a nearby system accelerates the conversation about the feasibility of interstellar missions. In recent years, technological advancements have brought us closer to realizing the dream of interstellar travel. Breakthroughs in propulsion technologies, like laser-powered sails, could one day make it possible to send small probes to Alpha Centauri and beyond. The Breakthrough Starshot project proposes launching small solar sail-powered probes toward Alpha Centauri at speeds up to 20% of the speed of light, potentially arriving in 2 decades, sending back images and data from the closest star system to Earth. While this concept remains a bold vision, it is grounded in real scientific principles. The discovery of potentially habitable worlds like S1 makes such missions seem less speculative. If a habitable moon exists around S1, as some scientists speculate, it could become a target for future exploration, potentially even hosting microbial life. However, interstellar exploration faces significant technological and logistical challenges. Current propulsion systems are insufficient for traveling to distant star systems within a reasonable time frame. Even with the best possible technologies, a journey to Alpha Centauri would take decades. The main obstacle is the vast distances involved. Even at speeds approaching the speed of light, it would take over 20 years to reach Alpha Centauri, and many more decades to explore its planets, moons, and the possibilities of extraterrestrial life. Sending humans to Alpha Centauri is an even greater challenge. The spacecraft would need life support systems capable of sustaining astronauts for an extended period. This would require innovations in closed-loop systems, energy generation, and radiation shielding, technological hurdles that have not yet been fully addressed. The psychological and physical effects of long-duration space travel are also significant concerns, as astronauts would be isolated from Earth for the duration of the journey. Nevertheless, the search for exoplanets and the discovery of potentially habitable worlds are pushing the boundaries of human ingenuity. As technology advances, the barriers to interstellar exploration will gradually fall. The insights gained from studying planets around stars like Alpha Centauri could drive the development of more efficient propulsion systems, advanced life support technologies, and spacecraft capable of sustaining human life on long-duration missions. For now, the focus remains on refining our ability to detect and study exoplanets. The James Webb Space Telescope, with its groundbreaking capabilities, has proven that it is possible to study distant planets in unprecedented detail. JWST's observations have shown that it is possible to capture faint signals from planets orbiting nearby stars, even in challenging environments like Alpha Centauri. With continued advancements in telescope technology, future observatories will push the limits of our ability to detect Earth-like planets, study their atmospheres, and assess their potential for supporting life. One of the next major milestones in exoplanet science will be the launch of the Nancy Grace Roman Space Telescope. Scheduled to launch in the mid-2020 ES, Roman's coronagraphic instrument will push the boundaries of what is possible in exoplanet imaging. Roman's capabilities will allow it to directly observe planets in the habitable zones of nearby stars and analyze their atmospheres for signs of life. This will mark a significant step forward in the search for habitable planets, as it will allow us to study the chemical composition of exoplanet atmospheres and search for biomarkers that could indicate the presence of life. As technology continues to evolve, new techniques will emerge that will allow us to detect smaller and fainter planets. Current methods, such as the transit method and radial velocity surveys, have already yielded thousands of exoplanet discoveries. These techniques, when coupled with advanced imaging technologies, will give us a more complete picture of the types of planets that exist beyond our solar system. While we are still in the early stages of this journey, the future of exoplanet science holds tremendous promise. The ultimate goal of exoplanet science is to answer one of humanity's most profound questions. Are we alone in the universe? If exoplanets exist, could they harbor life? And if so, what might that life look like? This quest for answers has been a driving force in astronomy for centuries, and now, with powerful telescopes like JWST, the possibility of finding life beyond Earth is closer than ever. The discovery of life elsewhere would be a momentous event, reshaping our understanding of biology, evolution, and the very nature of existence. Even if we do not find life immediately, the search for habitable worlds will continue to inspire future generations of scientists, engineers, and explorers. The technologies being developed to search for exoplanets will undoubtedly have broad applications, advancing our capabilities in remote sensing, data analysis, and even interstellar travel. In the end, the discovery of S1, whether it proves to be a planet or not, represents a pivotal moment in the search for other worlds. The quest for knowledge about Alpha Centauri and similar systems has opened new frontiers in astronomy, astrobiology, and space exploration. While the immediate future of interstellar exploration remains uncertain, the advances made through the study of exoplanets will continue to shape the way we approach space exploration for generations to come. Chapter 13. From Discovery to Exploration. As the discovery of S1 has shown, exoplanet science is advancing rapidly, and the implications of these discoveries are far-reaching. While the immediate goal is to continue refining techniques to detect and confirm planets like S1, the longer-term goal is to answer fundamental questions about the universe and humanity's place within it. With new telescopes, improved imaging techniques, and the ever-growing body of knowledge about distant worlds, the future of exoplanet exploration looks brighter than ever. Yet, as with every scientific breakthrough, this success opens new avenues of inquiry, presenting even more challenges, questions, and opportunities for the scientific community to explore. One of the most exciting prospects in the wake of S1's detection is the potential for studying exoplanetary atmospheres in great detail. The James Webb Space Telescope has already demonstrated its capability to analyze the atmospheres of distant exoplanets, providing vital information on their composition and habitability. However, the future holds even greater potential as more powerful telescopes come online and more advanced techniques are developed. The prospect of identifying biosignatures, molecules in an exoplanet's atmosphere that may indicate the presence of life, is a tantalizing goal. As scientists refine their methods of detecting these signatures, the search for life beyond Earth could become one of the most significant scientific quests of the coming decades. For now, the focus is on further observations of Alpha Centauri and other nearby star systems. The Alpha Centauri system remains one of the most scientifically important targets in the search for exoplanets. As the closest Sun-like star system to Earth, it offers unparalleled opportunities to study planetary systems in detail, potentially identifying planets in the habitable zone that could support life. JWST's capabilities have already proven effective in exploring this system, but as technology improves, future missions could provide even more detailed insights into the planets and moons orbiting Alpha Centauri A and B. One of the next great challenges for exoplanet science will be to determine whether planets like S1 have moons that could harbor life. While gas giants like S1 are unlikely to support life on their surfaces due to their lack of solid ground and extreme atmospheric pressures, their moons present an entirely different story. Moons of gas giants like Jupiter's Europa or Saturn's Titan are thought to have the potential to support life beneath their icy surfaces, in subsurface oceans warmed by internal heat. If S1 has moons that could harbor liquid water, it would represent one of the most exciting discoveries in the search for extraterrestrial life. The idea of studying exomoons around distant exoplanets introduces a new frontier in astronomical research. While current telescopes are not yet able to directly image exomoons, advances in imaging technology may soon make it possible. The next generation of space telescopes, including the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory, will be equipped with coronagraphs capable of detecting faint signals from exoplanets and their moons. These future missions could help astronomers identify and study exomoons in habitable zones, expanding our understanding of where life could exist beyond Earth. Another frontier of exploration will be the study of exoplanetary climates. While the discovery of a planet in the habitable zone of a star is an exciting first step, determining whether that planet has the right conditions to support life is a far more complex task. Scientists will need to study the planet's climate, atmospheric composition, and weather patterns in great detail. Factors such as temperature, atmospheric pressure, and the presence of greenhouse gases like carbon dioxide will be crucial for determining whether a planet could support liquid water on its surface, a key ingredient for life. Future missions will aim to study these factors in greater detail than ever before. The study of exoplanetary climates is likely to become a key area of focus in the coming years, especially as new technologies allow us to study the atmospheres of Earth-like exoplanets. The ultimate goal is to identify planets that not only exist in the habitable zone of their stars, but also possess the right conditions for life to thrive. If such planets are found, they could become prime targets for future space exploration missions. The next generation of telescopes will also allow astronomers to study planetary systems in greater detail. By observing how planets form and evolve, scientists can learn more about the processes that lead to the creation of habitable worlds. Understanding how planets like Earth form around Sun-like stars will be crucial for understanding how common life-supporting planets are in the universe. This knowledge could help guide future efforts to search for life beyond Earth, and may even provide insights into the history of our own solar system. As the search for exoplanets continues, the question of interstellar exploration will become increasingly important. While sending humans to distant star systems remains a distant dream, the development of advanced spacecraft capable of traveling at a fraction of the speed of light will be key to making this vision a reality. Projects like Breakthrough Starshot, which aims to send small laser-powered probes to Alpha Centauri, offer a glimpse into the future of interstellar exploration. These missions could provide humanity with the first close-up images of exoplanets, allowing us to study their surface conditions and even search for signs of life. The potential for interstellar exploration is vast, but it will require advancements in technology that we can only begin to imagine today. Propulsion systems that can reach significant fractions of the speed of light, advanced communication systems capable of transmitting data over light years, and life support systems capable of sustaining humans on long-duration missions will all be necessary to make interstellar exploration possible. While these challenges are immense, the pursuit of knowledge and the desire to explore the stars will continue to drive technological innovation. For now, the search for exoplanets and the study of distant star systems remain among the most exciting frontiers of science. The discovery of planets like S1 around Alpha Centauri represents a major step forward in our understanding of the universe, but it is only the beginning. As technology improves and new telescopes come online, the potential for discovering new worlds and perhaps new forms of life remains a tantalizing possibility. The next generation of astronomers, engineers, and explorers will continue to push the boundaries of human knowledge, striving to answer one of humanity's oldest questions: are we alone in the universe? Chapter 14: Legacy of Alpha Centauri. The journey to discover S1, whether it is ultimately confirmed as a planet or not, has already reshaped the scientific landscape of exoplanet research. The Alpha Centauri system, our closest stellar neighbor, has long been a focal point for astronomers who dream of exploring worlds beyond our own solar system. S1's potential detection, along with the groundbreaking techniques employed to observe it, opens the door to a new era in exoplanet science, one that could have far-reaching implications for humanity's understanding of the universe and our place in it. Regardless of whether S1 is confirmed, the methods developed to detect and study it will be pivotal in the future of exoplanet exploration. JWST's unprecedented sensitivity to exoplanetary signals has already changed the way astronomers approach the detection of distant worlds. The challenges faced in the search for S1, from the overwhelming brightness of Alpha Centauri A to the complexities of tracking its motion, have led to significant advancements in astronomical instrumentation and observational techniques. These breakthroughs will serve as the foundation for future exoplanet discoveries, allowing astronomers to peer deeper into distant star systems and uncover planets that were once thought impossible to detect. One of the most profound implications of the Alpha Centauri mission is its impact on the search for life beyond Earth. For centuries, astronomers have speculated about the existence of life on planets orbiting stars like our own Sun. The discovery of a potential planet in the habitable zone of Alpha Centauri A would not only mark a major milestone in exoplanet research, but could also provide the first concrete evidence that Earth-like conditions exist beyond our solar system. If confirmed, S1 would be the closest exoplanet ever discovered in the habitable zone of a Sun-like star, and the implications for astrobiology would be monumental. However, even without the confirmation of S1, the search for life beyond Earth will continue to evolve. The study of exoplanets is not just about finding Earth-like worlds. It's about understanding the diversity of planetary systems and the conditions that might support life. The possibility that life could exist on moons orbiting gas giants, as in the case of S1's potential moons, adds a new layer of complexity to our search for extraterrestrial life. Moons, particularly those in the habitable zones of their host planets, may be more conducive to life than previously imagined. This shift in focus could lead to the discovery of new environments where life could exist, not just on planets, but on their satellites as well. As the search for exoplanets continues, scientists are refining their methods for studying planetary atmospheres, particularly in the search for biosignatures, indicators of life. Advances in spectroscopic techniques, such as those that JWST is using to analyze exoplanetary atmospheres, will allow astronomers to detect chemical signatures that could reveal the presence of life. These signatures could include gases like oxygen, methane, or nitrous oxide, which are often associated with biological processes. The detection of such biosignatures, especially on planets in the habitable zone, would be a game changer, offering the first direct evidence of life beyond Earth. The implications of these discoveries go far beyond the realm of science. The search for life on other worlds challenges humanity's understanding of our place in the universe. Are we unique, or are there other intelligent civilizations out there waiting to be discovered? The discovery of extraterrestrial life, or even the detection of habitable environments, would force humanity to confront deep philosophical questions about our role in the cosmos. It would spark a new era of scientific, cultural, and even ethical debates about the implications of such discoveries. In addition to the scientific and philosophical implications, the discovery of exoplanets has the potential to revolutionize space exploration. As astronomers continue to detect planets in nearby star systems, the feasibility of interstellar exploration becomes increasingly realistic. The possibility of sending probes or even humans to nearby star systems, such as Alpha Centauri, could reshape the future of space travel. While we are still many years away from the technology needed for interstellar missions, the detection of potentially habitable exoplanets offers the promise of a tangible destination for future space explorers. Just as early astronomers once dreamed of traveling to the moon, the next generation may set their sights on the stars, with Alpha Centauri as the first stop. The success of the JWST and other space observatories also paves the way for future missions to study exoplanets. In the coming decades, new telescopes will continue to improve our ability to detect and study distant worlds. Ground-based telescopes, such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will provide additional capabilities for studying exoplanets and their atmospheres. These telescopes, when combined with the data from JWST and other space observatories, will allow for unprecedented studies of exoplanetary systems, enabling us to search for signs of life and better understand the conditions that make planets habitable. Beyond simply detecting exoplanets, future missions will focus on characterizing these worlds in greater detail. In the next few decades, we can expect to see missions that will not only confirm the presence of Earth-like planets, but will also study their atmospheres, compositions, and even their potential for supporting life. With each new discovery, the possibilities for space exploration and the search for extraterrestrial life expand, fueling humanity's drive to explore the stars. While the journey to discovering life beyond Earth is just beginning, the search for exoplanets has already opened up new frontiers of scientific inquiry. The detection of S1, whether confirmed as a planet or not, represents a significant leap forward in our understanding of the universe. The methods and techniques developed to observe Alpha Centauri and similar systems will continue to be applied to other star systems, bringing us closer to understanding the diversity of worlds that exist in our galaxy. The future of exoplanet science holds the potential to answer some of humanity's biggest questions, and with each new discovery, we move closer to uncovering the mysteries of the cosmos. Chapter 15. The Impact of JWST on Exoplanet Research. The James Webb Space Telescope, JWST, represents a monumental leap forward in astronomical technology and understanding. Initially designed to study distant galaxies, stars, and the early universe, JWST's groundbreaking success in exoplanet research, particularly with the potential discovery of S1, has expanded its role in ways previously unimaginable. As the most powerful space telescope ever built, JWST is revolutionizing our understanding of exoplanets and opening new doors for future discoveries. JWST's primary impact on exoplanet research lies in its ability to directly image planets around distant stars. Previous missions like Kepler and TESS detected exoplanets using indirect methods like measuring dimming, transits, or the wobble of stars, radial velocity. While these methods were successful, they couldn't provide detailed images of planets or their atmospheres, something JWST can do. JWST's advanced imaging capabilities in the infrared spectrum allow it to see through the cosmic dust that often obscures distant exoplanets. This ability to directly capture images of exoplanets and analyze their atmospheric composition is a game changer. By measuring light emitted or reflected by a planet, JWST can provide insights into its size, temperature, and atmospheric conditions, which are essential for determining whether a planet might be habitable. The coronagraphic technology on JWST is key for exoplanet research. It blocks out the star's light, allowing astronomers to study much fainter objects, like planets, nearby. This technology has allowed scientists to capture the first ever direct images of planets around stars as bright as Alpha Centauri. JWST's ability to observe in such a challenging environment, where the overwhelming light of the stars creates significant interference, has been a breakthrough. JWST is also advancing the study of exoplanetary atmospheres. By analyzing light passing through or reflected from a planet's atmosphere, astronomers can detect its chemical composition. Biosignatures, such as gases like oxygen, methane, and nitrous oxide, are key indicators of biological activity. JWST's advanced spectrographs can detect a range of molecules, providing vital information on the planet's potential for life. In the case of S1, JWST's mid-infrared instrument, MIRI, detected faint thermal radiation emitted by the planet. This type of observation is crucial because it allows scientists to study a planet's temperature and composition, even if it's not visible in visible light. For example, the thermal radiation detected by MIRI helped astronomers estimate that S1 is likely a gas giant with a temperature around 225 Kelvin. This information is vital for understanding the planet's environment and its potential for life, though it is unlikely to support life itself. The discovery of S1, whether confirmed as a planet or not, has highlighted the incredible potential of JWST for advancing exoplanet science. The techniques developed for Alpha Centauri will help confirm S1 or be applied to other nearby star systems. JWST's ability to observe distant planets in great detail will transform our understanding of how planets form, evolve, and interact with their host stars. It will allow us to probe the atmospheres of exoplanets and assess their potential for supporting life. The impact of JWST on exoplanet research goes beyond just discovering planets like S1. As scientists continue to explore the data coming from JWST, they are uncovering new aspects of planetary science. For example, JWST has already provided insights into the chemical makeup of distant exoplanets and the types of conditions that might support life. These findings will provide the foundation for future missions focused on detecting biosignatures in exoplanet atmospheres and identifying habitable worlds. The telescope's capabilities will also play a key role in understanding the diversity of planetary systems in the universe. Most of the exoplanets discovered so far are large gas giants, but JWST's ability to detect smaller planets, particularly those in the habitable zone of their stars, will help astronomers search for Earth-like worlds. These planets could be similar to Earth in size, composition, and distance from their stars, making them prime candidates for the search for life. Another frontier in exoplanet science is the study of planetary climates. Determining whether a planet has the right conditions to support life involves studying its climate, atmospheric composition, and weather patterns. Temperature, atmospheric pressure, and greenhouse gases like carbon dioxide are crucial for determining whether liquid water could exist on the surface. Future missions will focus on studying these factors in more detail, helping to identify planets in the habitable zone with the potential for life. The next generation of space telescopes, such as the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory, will build on JWST's work, enabling us to continue exploring exoplanets in even greater detail. These telescopes will have even more advanced coronagraphic systems, allowing them to study planets in the habitable zones of distant stars and analyze their atmospheres for signs of life. Ground-based observatories will also play a key role in the future of exoplanet science. The Extremely Large Telescope, ELT, currently under construction in Chile, will have a 39-meter primary mirror, allowing it to study exoplanets with greater precision than JWST. ELTs will work in tandem with space-based telescopes, providing complementary data to help refine our understanding of exoplanets. These telescopes will track exoplanets with greater precision, and their advanced spectroscopic instruments will allow for detailed analysis of planetary atmospheres. While JWST has already made significant strides in exoplanet research, its success will pave the way for future space missions. The next generation of telescopes will continue to improve our ability to detect and study exoplanets, particularly those in the habitable zone. These future telescopes will provide more detailed data on planetary atmospheres, compositions, and climates, bringing us closer to answering one of humanity's oldest questions: are we alone in the universe? Chapter 16: Alpha Centauri and Beyond. The idea of exploring Alpha Centauri and other distant star systems has been a tantalizing prospect for astronomers and science fiction enthusiasts for centuries. But with the groundbreaking discoveries made by the James Webb Space Telescope, JWST, and other modern observatories, the possibility of interstellar exploration is slowly moving from the realm of fantasy to the realm of scientific plausibility. As we learn more about nearby star systems like Alpha Centauri, the dream of exploring worlds beyond our solar system could soon become a reality. While current technology is far from capable of sending humans to Alpha Centauri, recent advancements in propulsion technologies and interstellar mission planning offer a glimpse into the future of interstellar travel. The detection of planets like S1 around Alpha Centauri A and the possibility of habitable moons around gas giants like S1 has added urgency to the discussion of interstellar exploration. These discoveries provide a concrete target for future space missions, one that could revolutionize our understanding of exoplanets and even life beyond Earth. The most immediate focus of interstellar exploration is the development of technologies capable of reaching nearby star systems. The idea of sending humans to Alpha Centauri remains far off, but the possibility of sending unmanned probes to study distant worlds is becoming more feasible. One of the most promising initiatives in this area is the Breakthrough Starshot project. This ambitious mission aims to send small, lightweight probes to Alpha Centauri at speeds up to 20% of the speed of light, potentially reaching the star system in just over 2 decades. These probes, powered by lasers and equipped with small cameras and sensors, would provide humanity's first close-up images of exoplanets in Alpha Centauri and other nearby star systems. Breakthrough Starshot is just one example of the growing interest in interstellar exploration. As new technologies are developed, the feasibility of sending probes to distant star systems becomes more likely. For now, the focus is on improving propulsion systems and developing spacecraft that can travel at a significant fraction of the speed of light. Advances in laser propulsion, which could propel small probes to interstellar speeds, are one area of particular interest. This technology, if perfected, could provide a viable means of sending probes to Alpha Centauri and other nearby stars, opening up new frontiers of space exploration. While the technology to send humans to Alpha Centauri is still in the early stages, the detection of planets like S1 in the habitable zone of Alpha Centauri A has brought the possibility of interstellar exploration closer. If future observations confirm the presence of moons around S1, this could become a prime target for future missions. Moons of gas giants, like Titan and Europa in our solar system, have already been identified as some of the most promising locations for extraterrestrial life. A similar moon orbiting S1, located within the habitable zone of its parent star, could harbor conditions suitable for life. The possibility of exploring such moons presents a new frontier in the search for life beyond Earth. If S1's moons are confirmed to support liquid water, they would become some of the most significant targets for astrobiology research. The discovery of microbial life on such a moon would be a historic event, fundamentally altering our understanding of life in the universe. The study of these moons could also reveal insights into the conditions necessary for life to emerge and survive in extreme environments. While sending humans to Alpha Centauri is not yet feasible, the technology needed for interstellar travel is advancing. The development of faster propulsion systems, like the use of light sails, could one day make interstellar missions possible. Light sails are thin, reflective sails that use the pressure of light from a star or laser beam to propel spacecraft. These sails, if scaled up, could potentially carry probes to Alpha Centauri at a significant fraction of the speed of light. If successful, light sail technology could open up new possibilities for interstellar exploration. The challenge of reaching Alpha Centauri, however, is not just technological. It also involves understanding the vast distances involved and how long such a journey would take. Even with light sail technology, a probe traveling at 20% of the speed of light would take over 20 years to reach Alpha Centauri. For human missions, the timescales would be much longer, and new methods of life support, resource management, and crew endurance would need to be developed. The isolation of interstellar missions would also pose significant psychological challenges for astronauts, as they would be far beyond the reach of Earth's communication networks and support systems. The ultimate goal of interstellar exploration is to send humans to distant star systems, but this vision is still a long way off. In the meantime, the study of exoplanets like S1 and the search for habitable moons around gas giants will continue to drive research and exploration. As technology advances and our understanding of distant star systems improves, the possibility of interstellar travel will become more realistic. Missions to Alpha Centauri and other nearby stars may be a distant dream, but each new discovery brings us closer to making it a reality. In the years ahead, space agencies around the world will continue to develop new technologies and strategies for interstellar exploration. Whether through missions like Breakthrough Starshot, the development of advanced propulsion systems, or the study of habitable exoplanets, the future of interstellar travel holds enormous promise. As we learn more about the planets and moons around Alpha Centauri and other nearby stars, humanity will move closer to answering one of the most profound questions of all. What lies beyond our solar system? While the exploration of distant star systems remains an enormous challenge, the advances made in the study of exoplanets provide a clear path forward. The discoveries made by JWST, particularly the potential detection of S1 and its possible moons, mark a new chapter in the search for life beyond Earth. As we continue to study these worlds and develop the technologies necessary for interstellar exploration, the dream of reaching Alpha Centauri, and perhaps beyond, will move ever closer to reality. Chapter 17: How Exoplanet Discoveries Shape Our Understanding of the Universe. The study of exoplanets has irrevocably changed our understanding of the universe. What started as a speculative endeavor has evolved into one of the most exciting fields of astronomy. As more exoplanets are discovered, the lines between what we know and what we can imagine are continuously redrawn. The discovery of exoplanets such as S1, potentially orbiting Alpha Centauri A, is a perfect example of how these findings challenge our existing knowledge. Before modern space telescopes like JWST, finding Earth-like planets around stars so close seemed unattainable. Yet, these observatories now bring the impossible within reach, reshaping our perception of the cosmos. These discoveries strike at the heart of the age-old question: are we alone in the universe? The potential existence of Earth-like planets orbiting Sun-like stars raises the tantalizing possibility of extraterrestrial life. While many questions remain unanswered, planets like S1 fuel the search for habitable worlds. The idea that life could exist on moons orbiting gas giants like S1 further expands our understanding. Moons of gas giants like Europa in our solar system could support life beneath icy surfaces. If moons around S1 are found to harbor liquid water, they would become prime targets for future astrobiological research. As JWST continues to reveal exoplanet atmospheres, scientists can study the chemical makeup of these planets and search for biosignatures, gases like oxygen, methane, and nitrous oxide, indicative of biological processes. This capability is crucial for understanding a planet's potential to support life. The detection of gas giants like S1 challenges traditional models of planetary formation. While early models suggested that gas giants could only form at great distances from their stars, the discovery of such planets closer to their stars shows that planetary systems can evolve in unexpected ways. These findings are reshaping our understanding of planetary formation and the diversity of planetary systems. The continued exploration of exoplanets is central to understanding the potential for life in the universe. Future telescopes, like the Nancy Grace Roman Space Telescope and Habitable Worlds Observatory, will build on JWST's success, enabling scientists to study planets in greater detail. These telescopes will allow for the identification of Earth-like planets and the detection of biosignatures in their atmospheres, which will be crucial for the search for life. Ground-based observatories, such as the Extremely Large Telescope, ELT, will provide complementary capabilities, enabling detailed studies of exoplanets and their atmospheres. Together, space-based and ground-based telescopes will form the backbone of future exoplanet research, expanding our knowledge of planetary systems and the potential for life beyond Earth. The discovery of exoplanets like S1 is prompting a shift in how we view our place in the universe. For centuries, Earth was thought to be the center of the universe, the only planet capable of supporting life. But as we learn more about exoplanets, we realize that Earth may not be unique. While we haven't yet found life beyond Earth, the increasing number of habitable zone planets suggests that life-supporting conditions might be more common than we thought. The exploration of exoplanets is about more than finding new worlds. It's about understanding the forces that shape the universe. Each discovery raises new questions about the origins of life, the potential for other civilizations, and humanity's future. Whether we find life on exoplanets or not, the search is advancing our knowledge of the cosmos and driving technological innovation. As we push the boundaries of our understanding, we're opening new possibilities for space exploration, planetary science, and the search for extraterrestrial intelligence. The future of exoplanet research will continue to evolve. As new technologies and telescopes come online, we will deepen our understanding of planetary systems. The search for Earth-like exoplanets will intensify, and the quest for signs of life beyond Earth will drive the next era of space exploration. With each discovery, we move closer to answering one of humanity's most profound questions. Are we alone in the universe? Chapter 18: Future Missions and Their Role in Exoplanet Exploration. The future of exoplanet exploration lies not only in refining the techniques we use to study distant worlds, but also in the missions that are set to build on the foundations laid by the James Webb Space Telescope, JWST, and other current observatories. With the success of JWST's detection of potential exoplanets like S1 in the Alpha Centauri system, the next phase of planetary science is poised to take off, with new missions set to unlock even more secrets about exoplanets and their potential for supporting life. One of the most important aspects of future missions will be the continued development of space telescopes. Following in the footsteps of JWST, upcoming space observatories will focus on studying exoplanets with greater detail, offering better sensitivity and refining methods for identifying habitable worlds. The most promising of these upcoming missions is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. While Roman's primary mission is to carry out wide-field surveys of the universe, its secondary mission will be the study of exoplanets, particularly through the use of its powerful coronagraph, which will allow it to detect distant worlds even closer to their stars. This capability will make it an essential tool in the search for Earth-like planets and in the study of planetary atmospheres. Roman's coronagraph technology will also enable the detection of exoplanets that are too faint or too close to their stars for JWST's coronagraph to observe. Its precision will offer a crucial complement to JWST, which is optimized for observing faint, distant objects. Roman will focus on nearby star systems, where habitable zone planets are more likely to exist and be observable with current technology. As it uncovers new exoplanets, it will help to refine our understanding of how planets evolve, how they interact with their host stars, and whether any may host the conditions necessary for life. Another key future mission is the Habitable Worlds Observatory, HWO, which has been proposed as the next step in the search for life beyond Earth. The HWO would be designed specifically to directly image Earth-like exoplanets in the habitable zone of their stars and analyze their atmospheres for signs of life. This mission would be a game-changer, as it would allow us to study Earth-sized planets around stars similar to our Sun, something that has yet to be fully realized. The HWO would focus on finding small, rocky planets that are in the right distance from their stars to support liquid water, one of the key ingredients for life as we know it. The HWO's main goal would be to use advanced coronagraphy and spectroscopic techniques to observe these Earth-like planets in the habitable zone. With its advanced instruments, HWO would be able to detect even the faintest signals coming from a planet's atmosphere, such as gases like oxygen, methane, and carbon dioxide, which are often associated with biological processes. This would open a new frontier in the search for extraterrestrial life by allowing us to study the atmospheres of planets that are similar in size and temperature to Earth, potentially even revealing biosignatures that indicate the presence of life. On the ground, the upcoming Extremely Large Telescope, ELT, will revolutionize exoplanet research. The ELT, currently under construction in Chile, will have a 39-meter primary mirror, 4 times the size of any existing optical telescope. Its size and sensitivity will allow it to study exoplanets in unprecedented detail, particularly smaller planets that JWST cannot observe. The ELT will focus on planets that are much closer to their stars, where conditions could potentially support life. With its advanced adaptive optics system, the ELT will be able to capture detailed images of exoplanets, even blocking out the light from their stars to study their atmospheres. The ELT's coronagraph will be key to its ability to directly image exoplanets, especially those in the habitable zone. Like JWST and Roman, the ELT will use coronagraphic technology to block the intense light from a star, allowing it to observe faint exoplanets and analyze their atmospheres for signs of life. In combination with other instruments, the ELT will be able to study the chemical composition of exoplanetary atmospheres and measure their temperatures, providing valuable insights into their potential habitability. In addition to space-based and ground-based telescopes, advancements in data processing and machine learning will play a crucial role in future exoplanet research. As the volume of data generated by telescopes like JWST and Roman increases, the ability to analyze that data efficiently and accurately becomes ever more important. Machine learning algorithms, which are already being used to identify exoplanets in large datasets, will become even more sophisticated, enabling astronomers to spot exoplanets more quickly and analyze their characteristics with greater precision. Furthermore, future missions will continue to focus on studying exoplanetary systems that are similar to our own, including the search for moons around gas giants like S1. Moons, particularly those that are within the habitable zones of their planets, could be some of the most promising locations for life. By studying the moons of gas giants, scientists hope to discover environments that are capable of supporting life, whether beneath icy surfaces or in subsurface oceans, like those found on Jupiter's moon Europa and Saturn's moon Enceladus. The next generation of telescopes will allow scientists to study these moons in greater detail, helping to determine whether they could harbor life. One of the biggest challenges in exoplanet exploration, particularly when it comes to studying moons around distant planets, is the resolution of current telescopes. Even with the most advanced instruments such as JWST and the ELT, moons around exoplanets are still too small to directly observe. However, as technology improves, the resolution of future telescopes will continue to improve, making it possible to directly image moons around exoplanets. This will be a crucial step in the search for extraterrestrial life, as moons could provide environments that are more favorable for life than their host planets. Finally, interstellar missions will continue to inspire the next generation of space explorers. While the technology for human interstellar travel is still far from reality, missions like Breakthrough Starshot are pushing the boundaries of what's possible. These missions aim to send small, lightweight probes to Alpha Centauri using laser-driven sails to reach 20% of the speed of light. These probes would provide humanity's first close-up images of exoplanets and could help answer some of the most profound questions about life beyond Earth. As our understanding of exoplanets continues to grow, the possibility of interstellar exploration will become more realistic. The discoveries made by JWST, Roman, the ELT, and future space missions will provide the foundation for sending probes to distant star systems, bringing us closer to exploring the stars. The search for exoplanets has already expanded the scope of space exploration, and in the coming decades, new missions will continue to push the boundaries of what we can achieve. Chapter 19: The Search for Habitable Worlds. For centuries, humanity has wondered whether we are truly alone in the universe. With the discovery of thousands of exoplanets, particularly those in the habitable zone of their stars, the dream of finding another Earth-like world has moved from the realm of science fiction to a tantalizing scientific reality. As astronomical technology advances, the search for habitable worlds has become one of the most profound and pressing questions in modern science. At the heart of the search is the concept of the habitable zone, the region around a star where conditions are right for liquid water to exist on a planet's surface. This zone, often referred to as the Goldilocks zone, is considered the most likely area where life as we know it could thrive. The discovery of planets in this zone has become a focal point for astrobiologists and astronomers, as these planets have the potential to support life. JWST's ability to detect exoplanets in the habitable zone is revolutionizing our search for life beyond Earth. The telescope's advanced capabilities allow it to observe distant exoplanets in greater detail than ever before, analyzing their atmospheres for signs of life. One of the most exciting aspects of this search is the ability to study the chemical composition of exoplanetary atmospheres. By analyzing the light that passes through or reflects off a planet's atmosphere, scientists can detect gases that are indicative of biological activity, such as oxygen, methane, and carbon dioxide. The first step in finding habitable worlds is identifying planets in the habitable zone of their stars. While many exoplanets have been discovered, finding those that lie within their star's habitable zone is more challenging. JWST's ability to directly image exoplanets, particularly those in the habitable zone, allows astronomers to identify these worlds with greater precision. The telescope's sensitivity to infrared light enables it to study the thermal radiation emitted by planets, providing crucial data on their temperature, composition, and potential for life. One of the most promising discoveries made by JWST is the detection of S1, a planet that may be orbiting Alpha Centauri A in the habitable zone. This discovery is particularly exciting because Alpha Centauri is the closest Sun-like star to our own, located just over 4 light-years away. The proximity of Alpha Centauri makes it an ideal target for the search for life, as the planet's proximity allows us to study it in unprecedented detail. S1, if confirmed as a planet, would provide astronomers with a unique opportunity to study a potentially habitable world around a star so similar to our Sun. While S1 is an exciting candidate, it is important to note that not all planets in the habitable zone are capable of supporting life. Factors such as atmospheric composition, magnetic fields, and geological activity all play a critical role in determining whether a planet can support life. For example, gas giants like S1 are unlikely to harbor life on their surfaces due to their lack of a solid surface and extreme atmospheric conditions. However, their moons may offer more promising conditions for life. Just as Jupiter's moon Europa and Saturn's moon Enceladus are considered potential locations for life due to their subsurface oceans, moons orbiting gas giants in the habitable zone of their stars could also provide environments suitable for life. The detection of exoplanets like S1 has also led to a rethinking of how planets form and survive in different stellar environments. Alpha Centauri A, for example, is a binary star system, and the presence of a second star, Alpha Centauri B, creates unique challenges for planetary formation. In binary star systems, the gravitational pull of both stars can disrupt the formation of planets, making it difficult for planets to form and maintain stable orbits. Despite this, the discovery of S1 suggests that planets can survive in such environments, which challenges previous assumptions about the habitability of planets in binary star systems. The search for habitable exoplanets is not just about finding planets that may host life. It is also about understanding the conditions that make life possible. The discovery of planets in the habitable zone of their stars has spurred research into what makes a planet habitable. Scientists are studying factors such as the planet's distance from its star, the composition of its atmosphere, and its climate. These factors are essential for determining whether a planet can support life, and studying them will help us understand the conditions that are necessary for life to emerge and thrive. While the detection of exoplanets in the habitable zone is a significant step forward, there is still much to learn about the conditions required for life. The study of exoplanet atmospheres, for example, is still in its early stages. JWST's ability to study the chemical composition of exoplanet atmospheres is a crucial breakthrough, but it will take years of data collection and analysis before we can fully understand the potential for life on these planets. In the meantime, the search for habitable worlds will continue, with future telescopes and missions designed to improve our ability to detect and study exoplanets. In the coming decades, astronomers will continue to study exoplanets and refine their methods for detecting habitable worlds. The search for life beyond Earth will drive much of this research, as scientists look for planets with conditions that are similar to those on Earth. While the discovery of an Earth-like planet in the habitable zone of a star is a monumental achievement, it is only the beginning of a long and challenging search for life beyond our solar system. The future of exoplanet exploration holds great promise. As technology advances and new telescopes are developed, our ability to detect and study exoplanets will continue to improve. The search for habitable worlds will become more focused, and future missions will be able to study planets in greater detail than ever before. Whether or not we find life on these worlds remains to be seen, but the journey to answer that question will undoubtedly shape the future of astronomy and space exploration. The study of exoplanets is not just a scientific endeavor, it is a deeply philosophical one as well. The search for life beyond Earth raises fundamental questions about our place in the universe and the nature of life itself. Are we the only ones, or are there other civilizations out there waiting to be discovered? As we continue to explore distant worlds, the answers to these questions may bring us closer to understanding our place in the cosmos. Chapter 20: The Role of JWST in Shaping Interstellar Discovery. The James Webb Space Telescope, JWST, represents the cutting edge of astronomical technology, designed to revolutionize our understanding of the cosmos. Beyond its critical role in studying distant galaxies, star formation, and the early universe, JWST's capabilities extend to the direct study of exoplanets and the search for signs of extraterrestrial life. This expansion of JWST's mission has opened up exciting new possibilities for interstellar discovery, helping to redefine our place in the universe. As humanity's most powerful space telescope, JWST is not only providing breathtaking images of distant cosmic phenomena, but also offering profound insights into planetary systems beyond our own. The discovery of planets like S1 in the habitable zone of Alpha Centauri A is just the beginning of what JWST is capable of. By peering deeper into star systems, analyzing atmospheres, and observing previously unreachable celestial objects, JWST is enabling a new era in the study of planets and the potential for life in other star systems. The ultimate goal of JWST's mission is to expand our understanding of exoplanets by analyzing their compositions, climates, and atmospheres. One of the key capabilities of JWST is its ability to capture light in the infrared spectrum, which is essential for studying exoplanets that are too faint to be seen in visible light. By detecting thermal emissions from exoplanets, JWST can analyze the heat signatures that give scientists vital information about a planet's atmospheric composition, surface temperature, and even potential signs of life. The search for habitable planets has long been a driving force in exoplanet science. The detection of planets in the habitable zone of their stars, where conditions could support liquid water, is of particular interest to astronomers. With the advent of JWST, the goal of finding Earth-like planets in the habitable zone has become much more attainable. The telescope's advanced instruments, such as its mid-infrared instrument, MIRI, allow for precise measurements of exoplanet temperatures, allowing astronomers to determine whether a planet lies in the so-called Goldilocks zone, where conditions are just right for life to thrive. For decades, astronomers have speculated about the existence of Earth-like planets in nearby star systems, particularly around our closest stellar neighbors, such as Alpha Centauri. This star system has long captured the imagination of both scientists and the general public. As the closest Sun-like stars to our own Sun, Alpha Centauri's planets, if they exist, offer the most promising targets for the search for extraterrestrial life. JWST's ability to directly observe planets in this system, such as S1, is one of the most significant breakthroughs in exoplanet research. With its unprecedented sensitivity and advanced technology, JWST can study these planets in detail, helping us understand how planets form, evolve, and potentially sustain life. However, the search for habitable exoplanets is not just about finding planets that could support life. It is also about understanding the conditions that make life possible. The study of planetary atmospheres is crucial in determining whether a planet has the right conditions for life. Atmospheric composition, especially the presence of gases like oxygen, methane, and carbon dioxide, can reveal whether a planet is capable of sustaining life. JWST's spectroscopic capabilities enable astronomers to study these atmospheres in unprecedented detail, offering the best chance yet of detecting biosignatures or signs of biological activity on distant worlds. One of the most important contributions of JWST to the search for life beyond Earth is its ability to study planets in the habitable zones of their stars. By focusing on planets that are located in these zones, JWST is providing valuable insights into the conditions that make life possible. While many of the planets JWST studies will be gas giants like S1, there is always the potential that some of these planets may have moons that could host life. For instance, the moons of Jupiter and Saturn, such as Europa and Enceladus, are prime candidates for harboring life due to their subsurface oceans. The discovery of moons like these orbiting gas giants in the habitable zone would provide the most promising locations for the search for extraterrestrial life. While JWST's primary mission focuses on studying distant objects in the universe, its capabilities also extend to more immediate goals, such as the study of nearby star systems. Alpha Centauri is just 4.37 light-years from Earth, making it the closest star system to our own. This proximity makes it an ideal target for JWST's exoplanetary research, allowing for detailed studies of planets like S1. However, Alpha Centauri presents unique challenges for JWST, primarily due to the brightness of its stars and their complex binary nature. These challenges have required the development of innovative techniques, such as the coronagraph, which blocks out the light of the stars to allow for the detection of much fainter objects, such as planets and moons. The study of Alpha Centauri, as well as other nearby systems, will help us understand the broader implications of planetary science and how planets form in different environments. As we continue to observe star systems like Alpha Centauri, we will gain insight into how planetary systems evolve, how planets interact with their host stars, and what factors contribute to the formation of habitable planets. Another important aspect of JWST's work is its contribution to the broader understanding of stellar evolution. By studying how stars like Alpha Centauri form and evolve, we can learn more about the conditions that exist in star systems at different stages of their life cycles. This knowledge can help inform our understanding of the potential for life in other parts of the universe, as well as the conditions that exist on planets and moons in different stages of their formation. As we move forward into a new era of astronomical discovery, JWST will continue to play a critical role in shaping our understanding of exoplanets, star systems, and the potential for life beyond Earth. The groundbreaking discoveries made by JWST, such as the detection of S1 and other exoplanets in the Alpha Centauri system, will provide the foundation for future missions and help guide the search for habitable worlds. While the idea of traveling to distant stars may seem far-fetched, the discoveries made by JWST are paving the way for interstellar exploration. As future missions continue to refine the technology for interstellar travel, the discoveries of planets in nearby star systems will provide valuable targets for future probes and spacecraft. These discoveries will inform the development of propulsion technologies, communication systems, and other essential technologies needed for human exploration of other star systems. In the coming decades, JWST will continue to make groundbreaking discoveries that will transform our understanding of the universe. As new telescopes and missions come online, the study of exoplanets will continue to evolve, and the search for habitable worlds will become more focused. Whether we find life on these distant planets or not, the search will continue, driving the next era of space exploration. Chapter 21: The Quest for Life Beyond Earth. The quest for life beyond Earth has captivated scientists, philosophers, and the public alike. For centuries, we've wondered if there are other worlds where life might exist. With the discovery of thousands of exoplanets, especially in their stars' habitable zones, the search for extraterrestrial life has shifted from speculation to scientific pursuit. This shift is driven by technological advancements, including the James Webb Space Telescope, JWST, which is revolutionizing our ability to detect and study exoplanets in unprecedented detail. The goal of exoplanet research is to determine whether life exists beyond Earth. Planets in the habitable zone of their stars are prime targets for astrobiological research. While finding such planets doesn't guarantee life, it opens exciting possibilities. JWST's ability to study exoplanet atmospheres is critical in this search. By analyzing the light passing through or reflecting off an atmosphere, JWST can detect gases like oxygen, methane, and carbon dioxide, often associated with biological activity. JWST's spectroscopic capabilities allow astronomers to study exoplanet atmospheres in unprecedented detail, providing crucial data about their potential for life. One of the most exciting findings is the potential detection of moons around gas giants in habitable zones, similar to Europa and Enceladus in our solar system. Moons could offer the right conditions for life, particularly in subsurface oceans. While planets like S1 may not support life on their surfaces, their moons may provide hospitable environments. The discovery of such moons would be significant for astrobiology, as they could harbor life in environments radically different from Earth's. The detection of exoplanets in the habitable zone is just the beginning. As we continue to study these planets, we will learn more about the factors that influence the potential for life. The composition of a planet's atmosphere, surface conditions, and ability to retain water are essential factors in determining whether life could exist there. JWST's ability to study the chemical makeup of exoplanetary atmospheres will provide valuable insights into their habitability. The discovery of exoplanets has also challenged our understanding of what makes a planet habitable. While much of the research has focused on Earth-like conditions, we now know that life could potentially exist in environments very different from our own. Extremophiles, organisms that thrive in extreme conditions on Earth, suggest that life might not require the same conditions we have on Earth. This realization broadens the scope of where we might find life, on both exoplanets and moons in our own solar system. The study of exoplanets is transforming astrobiology. JWST is enabling the search for life beyond Earth by studying exoplanet atmospheres for signs of biological activity. While we haven't yet found definitive evidence of life, the discovery of exoplanets like S1 raises the exciting possibility that life could exist elsewhere. As technology improves, our ability to detect and study exoplanet atmospheres will grow, moving us closer to answering whether life exists beyond Earth. The future of astrobiology relies heavily on exoplanet research. The next generation of telescopes, including the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory, will build on JWST's work to directly image Earth-like planets and analyze their atmospheres for signs of life. The study of exoplanetary atmospheres is crucial to understanding the conditions necessary for life and will guide the search for extraterrestrial biosignatures. In the coming decades, space-based and ground-based telescopes will continue to provide data on exoplanets and moons, expanding our knowledge of where life might exist. As new technologies come online, the search for habitable exoplanets will become more focused, and our ability to detect biosignatures will improve. The search for life beyond Earth is one of the most profound questions in science, and exoplanet research is driving this search forward. By studying exoplanet atmospheres, we are not just looking for signs of life, we are learning about the conditions that make life possible. Whether we find life or not, the ongoing study of exoplanets will continue to inform our understanding of the universe and our place in it. Chapter 22: The Legacy of JWST. The James Webb Space Telescope, JWST, is not just another space observatory. It is a transformative tool that is redefining our understanding of the universe. As the most powerful space telescope ever built, JWST has already begun to unravel the mysteries of distant galaxies, star formation, and exoplanet research. However, its legacy goes beyond just its groundbreaking observations. It is shaping the future of space exploration, influencing the direction of future missions, and the way we approach the search for life beyond Earth. JWST's legacy will be defined by the answers it provides to some of the most fundamental questions in astronomy. How did the universe form? Are we alone? What does the future hold for planetary exploration? The telescope's ability to look deeper into the universe than any of its predecessors has provided us with unprecedented insights into the formation of galaxies, stars, and planetary systems. But its work is far from over. The discoveries made by JWST will continue to guide future space missions and shape the field of astrophysics for decades to come. One of the key areas where JWST is shaping future space exploration is in the study of exoplanets. The detection of planets in the habitable zones of their stars, such as the potential planet S1 orbiting Alpha Centauri A, marks a significant leap forward in our understanding of planetary systems. JWST's ability to study exoplanet atmospheres in detail has opened up new avenues for the search for life beyond Earth. Its advanced spectroscopic capabilities allow astronomers to study the chemical composition of exoplanet atmospheres, searching for biosignatures, gases like oxygen and methane that could indicate the presence of life. In the future, the technology developed for JWST will serve as the foundation for even more advanced missions. The discovery of exoplanets, especially those in the habitable zone, has prompted the development of missions aimed at studying these worlds in more detail. For instance, the proposed Habitable Worlds Observatory, HWO, will focus specifically on directly imaging Earth-like planets and studying their atmospheres. This mission will build on JWST's work by refining the techniques used to detect planets and study their potential for supporting life. As the search for habitable exoplanets becomes more focused, missions like HWO will play a crucial role in advancing our understanding of what makes a planet truly capable of supporting life. In addition to studying exoplanets, JWST's discoveries are also paving the way for interstellar exploration. While human missions to other star systems are still far from reality, the discoveries made by JWST are driving the development of the technologies needed for interstellar travel. The detection of planets like S1, located just over 4 light-years away, has brought interstellar exploration into the realm of possibility. Missions like Breakthrough Starshot, which aims to send small laser-powered probes to Alpha Centauri, are now being given concrete objectives as scientists gain a clearer understanding of what exists at these distant star systems. JWST's work has also laid the groundwork for future space missions by advancing the technology needed to observe distant objects with unprecedented precision. The telescope's ability to detect faint signals from distant galaxies and exoplanets has set new standards for what future telescopes and space observatories will need to achieve. The technologies developed for JWST, including its advanced imaging techniques, coronagraphs, and spectrometers, will serve as the foundation for future space missions, enabling the detection and study of exoplanets, stars, and galaxies with even greater accuracy. The James Webb Space Telescope has also influenced the design of upcoming space missions in terms of data processing. The immense amount of data generated by JWST requires new techniques for handling and analyzing it. The complex image processing methods developed to deal with JWST's data, including the use of reference star differential imaging and principal component analysis, have set new standards for data reduction. These methods will be applied to future missions, allowing astronomers to extract meaningful information from the vast amount of data generated by future telescopes. In addition to its impact on future missions, JWST is reshaping the way scientists approach space exploration. The discoveries made by the telescope have prompted new research into the origins of the universe, the formation of galaxies, and the conditions necessary for life. The study of exoplanet atmospheres, for example, has led to a new focus on astrobiology as scientists search for signs of life beyond Earth. JWST's ability to detect biosignatures and study the conditions of distant worlds has ignited a new era of research into the potential for life elsewhere in the universe. This focus on astrobiology will continue to guide future missions as we look for planets that might host life and explore the possibilities of life beyond Earth. As space exploration continues to evolve, JWST's legacy will extend beyond its direct discoveries. The telescope has set the stage for the next generation of space observatories and missions, pushing the boundaries of what is possible in astronomy. Its contributions to our understanding of exoplanets, galaxies, and the early universe will continue to shape the future of space exploration for years to come. The search for life beyond Earth, once a distant dream, is now becoming a tangible goal. JWST has provided the tools necessary for studying exoplanets and their potential to support life, and future missions will build on these advancements to continue this search. Whether we find life on another world or not, the discoveries made by JWST and the missions that follow will fundamentally change our understanding of the universe and our place in it. The legacy of the James Webb Space Telescope will not only be defined by its scientific discoveries, but also by the way it has transformed the field of space exploration. By pushing the boundaries of what is possible, JWST has set the stage for future missions that will continue to unravel the mysteries of the universe, bringing us closer to answering the age-old question: are we alone in the universe? Chapter 23. The significance of Alpha Centauri. Alpha Centauri, located just 4.37 light-years from Earth, holds a unique place in the cosmic landscape. As the closest star system to our own, it has long captured the imagination of astronomers and the public. For centuries, we've wondered about the potential for habitable planets and the possibility of life beyond Earth in this stellar neighborhood. Its proximity offers the first real opportunity to explore another star system and understand conditions that might support life. Alpha Centauri is a binary star system composed of two Sun-like stars, Alpha Centauri A and Alpha Centauri B, and a distant third member, Proxima Centauri. Alpha Centauri A and B orbit each other at about 23.6 astronomical units, AU, and share similar characteristics with our Sun. Proxima Centauri, a red dwarf, is located farther at around 13,000 AU. Proxima Centauri hosts at least two known exoplanets, including Proxima b, a planet located within the star's habitable zone. While Alpha Centauri A and B have been considered prime targets for habitable planets, Proxima b's discovery has added intrigue to the system. Proxima b has a mass comparable to Earth's and lies within the habitable zone. Though much remains uncertain about its conditions, its proximity to Earth has made it a key target for future exploration. With JWST, Proxima b and other exoplanets in Alpha Centauri can be studied in greater detail. The search for habitable planets around Alpha Centauri A and B has been challenging due to the star's intense brightness. Alpha Centauri A is one of the brightest stars in our sky, making it difficult to detect faint planets orbiting it. For decades, astronomers struggled to find planets here. However, JWST's technology has made it possible to detect exoplanets in such difficult environments. Its coronagraphs, which block out the star's light, allow it to observe faint objects like planets and moons. JWST's coronagraph technology has been crucial in the detection of potential planets like S1 in Alpha Centauri. By blocking out the bright star's light, JWST can study faint objects in its vicinity. The ability to study planets around Alpha Centauri A and B is pivotal for understanding planetary formation, evolution, and habitability. The proximity of Alpha Centauri means that discoveries here will provide valuable insights into the formation of planetary systems and the conditions that could support life. Alpha Centauri's significance also lies in its similarity to our Sun. Both Alpha Centauri A and B are similar to our star in size, temperature, and luminosity, making them ideal candidates for comparative studies. Studying planets orbiting these stars allows us to compare conditions on Earth with those on planets in similar stellar environments. If planets like S1 are confirmed to exist, they provide a benchmark for understanding how planets form and evolve around stars similar to the Sun. The system also holds importance for understanding planets in binary star systems. Historically, binary systems were thought to be inhospitable to planets because the gravitational influence of two stars would disrupt planetary orbits. However, the discovery of S1 challenges this assumption. S1's position within Alpha Centauri A's habitable zone shows that planets can indeed form and survive in binary systems. This discovery could change our understanding of planetary formation and survival in these environments. In addition to studying planets, Alpha Centauri offers opportunities to understand stellar dynamics. The gravitational interactions between Alpha Centauri A and B, along with the influence of Proxima Centauri, provide insights into the stability of planetary orbits and stellar system evolution. By studying these interactions, astronomers can refine their understanding of how planetary systems form and evolve over time. Alpha Centauri's proximity also makes it a prime candidate for interstellar exploration. While human missions to other star systems are still far from reality, the discoveries made by JWST are guiding the development of the technologies needed for interstellar travel. The detection of planets like S1, located just over 4 light-years away, brings interstellar exploration within the realm of possibility. Projects like Breakthrough Starshot, aiming to send probes to Alpha Centauri, are now focused on concrete objectives, as scientists learn more about what exists in these distant star systems. JWST's work has also set the foundation for future space missions. The telescope's ability to detect faint signals from distant exoplanets has set new standards for what future telescopes and observatories will need to achieve. The technologies developed for JWST, such as its advanced imaging techniques, coronagraphs, and spectrometers will be foundational for future missions to study exoplanets, stars, and galaxies in greater detail. Alpha Centauri continues to play a significant role in shaping the future of space exploration. The discoveries made by JWST and future missions will enhance our understanding of planetary systems and the potential for life. Whether or not we find life in Alpha Centauri, the knowledge gained from studying this system will have far-reaching implications for planetary science and interstellar exploration. As we continue to study Alpha Centauri and its planets, we will learn more about the conditions necessary for life and how planetary systems evolve in different stellar environments. Alpha Centauri may not just be a target for astronomical study, it could hold the answers to some of humanity's most profound questions about life beyond Earth. Chapter 24. What's next for space telescopes? As we stand on the precipice of a new era in space exploration, the future of exoplanet discovery and characterization is brighter than ever. The James Webb Space Telescope, JWST, has already set the stage by making unprecedented observations of distant planets and their atmospheres, unveiling a wealth of data that could significantly impact our understanding of exoplanets. Yet, even as we celebrate JWST's successes, we are reminded that its capabilities are just the beginning. The future of exoplanet exploration holds tremendous promise, with even more advanced telescopes and missions on the horizon that will push the boundaries of what we know about distant worlds. JWST's extraordinary capabilities have already changed the way we think about exoplanets. Its ability to detect faint signals from distant planets, study their atmospheres, and search for potential signs of life has opened a wealth of new opportunities in astrobiology. But JWST, while groundbreaking, is not designed to answer every question we have about exoplanets. It is limited by its field of view, observational time, and its inability to study planets in the visible light spectrum. Therefore, the next generation of space telescopes will need to overcome these limitations, enabling even more detailed exploration of exoplanets. One of the most exciting advancements on the horizon is the development of the Nancy Grace Roman Space Telescope, formerly known as WU-FIRST. Scheduled to launch in the mid-2020s, Roman will complement JWST's infrared capabilities by focusing on the visible and near-infrared wavelengths. Roman will carry out wide-field surveys of the sky, detecting exoplanets using both direct imaging and gravitational microlensing. The telescope's wide-field view will allow it to study a vast number of stars and exoplanets in different parts of the Milky Way, offering a new perspective on planet formation and evolution. Additionally, Roman's coronagraph, a device used to block out the light from stars and allow fainter planets to be observed, will enable detailed studies of exoplanet atmospheres. Roman's wide-field capability and advanced coronagraph make it particularly suited for studying exoplanets in a way that JWST cannot. While JWST excels at observing individual exoplanets and their atmospheres, Roman will focus on studying the broader population of exoplanets, including those that are too faint or too distant for JWST to detect. This will give scientists a more complete picture of exoplanetary systems and help answer questions about the diversity of planets in the galaxy. Another exciting project on the horizon is the Habitable Worlds Observatory, HWO, which is still in the conceptual stages. HWO would represent the next leap in exoplanet exploration, with a focus on directly imaging Earth-like planets in the habitable zones of nearby stars. Unlike JWST and Roman, which primarily observe exoplanets by detecting their emitted light or the way they affect their star's light, HWO would be capable of directly imaging planets and studying their atmospheres in detail. The goal is to observe planets that are similar to Earth, with conditions that might support life. HWO would be designed to search for signs of life on these planets by studying their atmospheric composition, looking for gases like oxygen, methane, and carbon dioxide, which are potential biomarkers. HWO would be a massive leap forward in the search for life beyond Earth, as it would be capable of observing planets in the habitable zones of their stars directly. By focusing on planets in the habitable zone, the telescope could detect biosignatures and gain insights into the conditions that make a planet truly capable of sustaining life. HWO would complement the work of JWST and Roman, focusing on Earth-like planets and advancing our understanding of the potential for life elsewhere in the galaxy. In addition to these missions, the continued development of ground-based observatories will play a crucial role in the future of exoplanet exploration. Large-scale observatories like the Extremely Large Telescope, ELT, currently under construction in Chile, will be able to observe exoplanets with unprecedented precision. ELT's giant 39-meter primary mirror will gather more light than all existing telescopes combined, allowing it to observe exoplanets with greater sensitivity than ever before. The ELT will be equipped with advanced imaging and spectroscopic capabilities, enabling it to study the atmospheres of exoplanets and detect biosignatures. Other ground-based projects, such as the Giant Magellan Telescope, GMT, and the 30-meter telescope, TMT, will also contribute to the future of exoplanet exploration. These telescopes will allow for more detailed observations of exoplanets, including the potential for imaging smaller, rocky planets in the habitable zones of nearby stars. By combining data from space-based telescopes like JWST and Roman with observations from these powerful ground-based observatories, astronomers will be able to study exoplanets in greater detail and refine their understanding of how planets form, evolve, and potentially support life. As we move into the next decade, one of the key goals in exoplanet research will be to identify Earth-like planets that could harbor life. While JWST and Roman will be able to detect planets and study their atmospheres, future missions like HWO will aim to find Earth twins, planets that are similar in size, composition, and distance from their star. The detection of these Earth-like planets would be a significant milestone in the search for extraterrestrial life, providing us with new targets for detailed observation, and possibly even future missions to study their atmospheres, surface conditions, and potential for life. In the long term, the development of interstellar probes, like the Breakthrough Starshot initiative, aims to send small spacecraft to nearby star systems, including Alpha Centauri, to study planets up close. While interstellar travel is still in the realm of science fiction, these efforts mark the beginning of an ambitious push to explore other star systems. By sending probes to study exoplanets directly, scientists could learn more about the conditions that make planets habitable, the potential for life on other worlds, and how planetary systems evolve over time. The future of exoplanet exploration is full of promise. With the continued advancement of space-based and ground-based observatories, the development of missions like HWO, and the potential for interstellar exploration, the search for life beyond Earth will continue to gain momentum. We are on the verge of answering one of humanity's most profound questions. Are we alone in the universe? The discoveries made by JWST, Roman, and the next generation of telescopes will provide the foundation for future missions to study exoplanets in greater detail. Whether we find life on these distant worlds or not, the search itself will drive the next wave of space exploration, pushing the boundaries of human knowledge and technology. The legacy of exoplanet research, supported by these powerful telescopes, will continue to shape our understanding of the cosmos and our place within it. Chapter 25. What the next decade holds for exoplanet exploration. The study of exoplanets is at the dawn of a new era, one that promises to reshape our understanding of the universe. As we look ahead to the next decade, the rapid advancements in technology, the success of telescopes like the James Webb Space Telescope, JWST, and the promise of upcoming missions herald a future filled with discoveries. The search for habitable exoplanets, the quest to answer the age-old question of whether we are alone, and the exploration of distant worlds are no longer distant dreams but pressing realities. The first phase of exoplanet research, which focused on detecting planets through methods such as the transit method and radial velocity, has already yielded remarkable results. Over 6,000 exoplanets have been confirmed, and astronomers have learned much about their diversity, from gas giants to potentially rocky Earth-like planets. However, detecting exoplanets is only the beginning of the journey. The next decade will be dedicated to understanding the atmospheres of these planets, searching for signs of habitability, and most excitingly, the potential for life beyond Earth. With JWST leading the charge, we are entering a period of unprecedented detail in our exploration of exoplanet atmospheres. JWST's ability to analyze the composition of distant exoplanet atmospheres, search for biosignatures, and study their physical characteristics will bring us closer than ever to understanding which of these planets might harbor life. Through its infrared capabilities, JWST will be able to detect gases like oxygen, methane, and carbon dioxide, key indicators of biological activity. These observations will allow scientists to begin piecing together the puzzle of habitability beyond our solar system. The next decade will also see the rise of new telescopes and missions designed to complement JWST's work. The Nancy Grace Roman Space Telescope, slated for launch in the mid-2020s, will focus on exoplanet discovery using gravitational microlensing and direct imaging. Roman's wide-field capabilities will allow it to survey large areas of the sky and detect planets that might be too faint or distant for JWST to observe. This will offer astronomers a more comprehensive view of exoplanetary systems, especially in our galactic neighborhood. Roman will also help bridge the gap between the discovery of exoplanets and the detailed study of their potential to support life. Its coronagraph will block out the overwhelming light from stars, allowing the telescope to capture the faint light from planets. By studying these faint planetary signals, Roman will be able to provide valuable data on the atmospheres of planets, including Earth-sized planets that might reside in the habitable zones of their stars. This will be a critical step in identifying which planets are prime candidates for future missions that aim to study their potential for habitability. Looking even further into the future, the Habitable Worlds Observatory, HWO, represents the next leap in exoplanet exploration. HWO, currently in the conceptual stages, is designed to directly image Earth-like planets in the habitable zones of nearby stars. Its advanced coronagraphs and spectrometers will enable scientists to study the atmospheres of these planets in unparalleled detail, searching for biosignatures and signs of habitability. HWO will take exoplanet research to the next level by not only identifying Earth-like planets, but also enabling scientists to directly observe their environments, potentially discovering signs of life or conditions that could support it. In addition to space telescopes, ground-based observatories are also set to revolutionize exoplanet exploration in the next decade. The Extremely Large Telescope, ELT, currently under construction in Chile, will feature a 39-meter mirror, making it the largest optical telescope in the world. ELT's advanced imaging capabilities will allow it to study exoplanetary atmospheres in more detail than ever before. With this telescope, astronomers will be able to directly image smaller exoplanets and study their atmospheres, including those in the habitable zone. The ELT will complement the work of space telescopes by providing a ground-based perspective on exoplanets and their potential for supporting life. Other observatories, such as the Giant Magellan Telescope, GMT, and the 30-meter telescope, TMT, will further extend our ability to observe exoplanets with incredible precision. These telescopes will be capable of measuring the chemical composition of exoplanet atmospheres, looking for signs of life or conditions conducive to it. Together with space-based observatories like JWST, these ground-based telescopes will form a powerful network of instruments that will allow us to observe exoplanets in a way that was previously unimaginable. Beyond the study of individual exoplanets, the next decade will also see the development of missions focused on planetary systems as a whole. In particular, scientists will continue to explore the possibility of moons around gas giants in the habitable zones of their stars. Moons like Europa, Enceladus, and Titan in our solar system have shown that even in the absence of a solid surface, life may exist in subsurface oceans. The discovery of moons around exoplanets that are located in the habitable zones of their stars could open up entirely new avenues for the search for life. The next decade in exoplanet exploration will also bring advancements in interstellar exploration. While current technology limits our ability to visit other star systems, initiatives like Breakthrough Starshot are pushing the boundaries of what's possible. Breakthrough Starshot aims to send small, lightweight probes to Alpha Centauri using laser propulsion to travel at a significant fraction of the speed of light. These probes would be able to reach Alpha Centauri within a few decades, giving us the first close-up images of exoplanets around another star. Although interstellar travel remains a distant goal, these initiatives mark the beginning of the technological developments necessary for future exploration of distant worlds. By the end of the next decade, we can expect a wealth of new discoveries that will transform our understanding of exoplanets and their potential to support life. With the combination of JWST, Roman, HWO, and ground-based observatories like the ELT, scientists will have the tools they need to detect and study exoplanets with unprecedented detail. The search for Earth-like planets, biosignatures, and extraterrestrial life will become one of the most exciting and high-priority areas of space exploration. The discoveries made during this period will shape the future of space missions, guiding the next generation of interstellar probes, planetary exploration, and even human space travel. The next decade will also witness an evolution in the way we think about the habitability of exoplanets. While the search for life has traditionally focused on finding Earth-like planets with similar conditions to our own, we are beginning to realize that life may not require the same conditions we experience on Earth. The discovery of extremophiles, organisms that thrive in extreme environments, has expanded our understanding of what constitutes a habitable environment. This realization will open up new possibilities for finding life in environments that are radically different from Earth's, whether on exoplanets, moons, or even in the atmospheres of distant gas giants. The future of exoplanet exploration is bright, and the next decade promises to be one of the most exciting periods in the history of space exploration. With new telescopes, advanced space missions, and a growing understanding of the conditions that make planets habitable, we are on the cusp of discovering worlds beyond our solar system that may harbor life. The search for life beyond Earth is no longer a distant dream. It is a tangible goal that we are closer to achieving every day.